Before the Big Bang, time and space as we know them did not exist. This idea can be difficult to grasp because everything we experience happens within time and space. The universe, from our perspective, has always had a past, present, and future. But if we go back far enough, past the formation of stars, galaxies, and even the first atoms, we reach a point where our understanding of physics breaks down. This is the singularity that led to the Big Bang. The singularity is a concept from Einstein's general relativity. I'd love to invite you to share in the comments where you're listening from and what time it is. It's incredible to think about how we're all connected through these stories and ideas. If you enjoy these thought-provoking explorations, consider subscribing to Tired Thinker so we can keep bringing you reflective narratives. Now, settle in, get comfortable, and let your imagination drift as we delve into the mind-boggling paradoxes and mysteries, describing a point where density and temperature become infinite. However, general relativity does not explain what actually happens at this extreme point. At this level, quantum mechanics, which governs tiny particles, should also play a role. But our current theories of physics cannot fully describe the moment before the Big Bang. Scientists believe a new theory, one that combines general relativity and quantum mechanics, is needed to explain it. One possibility is that the universe emerged from a quantum fluctuation. In quantum mechanics, empty space is not truly empty. It is filled with tiny energy fluctuations that appear and disappear constantly. Some physicists propose that one of these fluctuations could have led to the birth of the universe. This idea suggests that the universe may have originated from nothing in the way that virtual particles pop in and out of existence in quantum experiments. But this does not fully explain why this fluctuation happened or why it led to an entire universe instead of disappearing like most quantum events. Another idea is that the universe has always existed in some form. The Big Bang may not have been the absolute beginning, but rather a transition from a previous state. One model suggests that the universe goes through cycles of expansion and contraction. In this scenario, the universe expands for billions of years, then slows down and contracts into a dense state before expanding again. This is sometimes called the Big Bounce model. If true, it means that there was something before our current universe, but it does not tell us where the first cycle came from. Some theories suggest that our universe emerged from a larger, more complex system. The concept of a multiverse proposes that our universe is just one of many. In this view, universes could be constantly forming in a vast cosmic landscape, each with its own physical laws. This raises the question of what this larger system is made of and what rules govern it. Some scientists think our universe may have formed from a parent universe through a process similar to black hole formation. In this case, what we call the Big Bang could be the other side of a black hole in another universe. String theory offers another perspective. It suggests that the basic building blocks of reality are tiny vibrating strings rather than point-like particles. Some versions of string theory describe extra dimensions of space that are beyond our perception. In one model, our universe is a three-dimensional slice of a higher dimensional space. If another universe collided with ours in this higher dimensional space, it could have triggered the Big Bang. This model, known as the brane collision theory, suggests that what we think of as the beginning was actually an event in a much larger cosmic framework. Another possibility is that time itself may not have a true beginning. Some ideas in quantum gravity suggest that time is an emergent property rather than a fundamental one. In this view, asking what happened before the Big Bang may not make sense in the way we usually think. If time is not fundamental, then the idea of a before may not apply. This is similar to asking what is north of the North Pole. The concept of north exists only up to a certain point, and beyond that, the question loses meaning. Despite these theories, we still lack direct evidence of what came before the Big Bang. The cosmic microwave background radiation, the faint glow left over from the early universe, provides clues about what happened after the Big Bang, but it does not tell us about what came before. Some scientists search for patterns in this radiation that could suggest an earlier universe. Others look at the large-scale structure of the universe to find evidence of past cosmic cycles. But so far, no clear answer has emerged. Mathematics and physics provide models, but without direct evidence, it is difficult to determine which, if any, is correct. The nature of space and time itself may need to be redefined to fully answer the question. Some researchers explore the idea that space and time are not continuous, but instead made up of tiny discrete units, like pixels on a screen. If true, this could change the way we think about the origin of the universe. Instead of a single event, the beginning could be a gradual process emerging from deeper physical laws. The search for what came before the Big Bang continues through theoretical physics, observations of the cosmos, and experiments in particle physics. Scientists use telescopes to study the earliest light in the universe, hoping to find signals that point to a time before the known Big Bang. They also use particle accelerators to recreate conditions similar to the early universe, testing how matter and energy behave at extreme temperatures and densities. These efforts may eventually provide clues about the true origins of the universe. Understanding what came before the Big Bang may require a shift in how we define reality itself. If time and space had a beginning, then what set them in motion? If they always existed in some form, then what is the underlying structure that allows for their existence? These questions remain open, but each step in exploring them brings us closer to understanding the nature of the universe. The universe is vast beyond comprehension, but is it infinite or finite? This question has puzzled scientists and philosophers for centuries. If the universe is infinite, it has no edge and continues forever. If it is finite, it has a limit, but what lies beyond that limit? To explore this, we need to understand how scientists study the universe's size and shape. The cosmic microwave background radiation, the faint afterglow of the Big Bang, provides clues. Scientists have mapped this radiation and found that the universe appears nearly flat. In geometry, a flat surface can extend forever, suggesting an infinite universe. But appearances can be deceiving. A seemingly flat space can still be finite if it curves in a way we can't easily see, like how the surface of the Earth seems flat when you're standing on it, but is actually curved into a sphere. One way to imagine a finite universe is to picture a video game world. Some games use a technique where if you walk far enough in one direction, you eventually loop back to where you started. The game world feels infinite, but it's actually a closed system. Scientists propose something similar for space. If the universe is finite, traveling in one direction indefinitely might bring you back to where you began, though the distances involved are so immense that this effect would be impossible to observe within a human lifetime. Another way to test this is by looking at distant galaxies. If the universe were finite and closed, light from ancient galaxies might have circled around and reached us from multiple directions. So far, astronomers haven't found duplicate images of galaxies that would confirm this looping effect. This suggests either the universe is infinite or so large that the loops are beyond our observable reach. The concept of an infinite universe raises its own challenges. If space goes on forever, then every possible arrangement of matter must exist somewhere. That means there could be another version of you reading this right now in a galaxy unimaginably far away. It also means the number of galaxies, stars, and planets would be endless. But infinity is tricky. Even in an infinite universe, certain things might not repeat. The laws of physics might change in distant regions, leading to entirely different forms of matter and energy. A finite universe makes more sense in some ways. If the universe had a beginning, as the Big Bang theory suggests, then it seems logical that it also has a size that we could, at least in theory, measure. The problem is that space isn't just sitting still. The universe is expanding, and it's doing so at an accelerating rate due to dark energy. If the universe is finite, is it expanding into something, or is space itself stretching? Current models suggest space itself is stretching rather than expanding into anything, which complicates the question. Observations of cosmic expansion suggest that if the universe is finite, it must be much larger than what we can see. The observable universe is about 93 billion light-years across. That's just the part we can detect based on how far light has traveled since the beginning of time. Beyond that, the rest of the universe remains unknown. If the universe is infinite, then there is no edge. It simply keeps going. But if it's finite, then there must be a boundary of some kind. The nature of that boundary is unclear. It might be a region where space curves back on itself, or it could be something stranger. There's also the possibility that the universe is finite in one way, but infinite in another. Think about the surface of a balloon. It's finite in the sense that you can measure its total area, but it has no edges. If you lived on this surface, you could travel forever without ever reaching an end. Some cosmologists propose that the universe might be shaped like a higher dimensional version of this, meaning it's finite but unbounded. Mathematics allows for models where the universe has unusual shapes. Some suggest it could be shaped like a torus, which is like a donut. In this model, if you traveled far enough in one direction, you'd loop back around, but the way space curves would make this difficult to detect. Another possibility is a hyperbolic shape, which would mean the universe has an overall negative curvature. One of the biggest challenges in answering this question is that we can only observe a small part of the universe. The speed of light limits how far we can see. No matter how powerful our telescopes become, we will never see beyond a certain distance, because light from those regions hasn't had enough time to reach us. This means we may never know for sure if the universe is infinite or just extremely large. The idea of an infinite universe also has implications for physics. If space is truly infinite, then any event that can happen must happen somewhere. This would support the idea of a multiverse, where there are infinitely many versions of reality. Some scientists argue that quantum mechanics allows for multiple possible outcomes of events, and if the universe is infinite, then every possible outcome must exist somewhere. This means there could be countless versions of history playing out differently across the cosmos. A finite universe avoids some of these paradoxes. If space has a definite size, then there is a limited number of ways matter can be arranged. This would mean that while the universe is vast, there are limits to what can exist. It would also mean that the Big Bang created a specific, measurable space rather than an endless expanse. Recent studies have focused on measuring the overall curvature of space to determine whether the universe is finite or infinite. So far, results indicate that the universe is very close to flat, which could support either possibility. If it's perfectly flat, it could be infinite. If it has even a slight curvature, then it must be finite, but so large that we can't detect the curvature. Another approach involves looking at how space expands. If the universe is infinite, its expansion would continue indefinitely without ever reaching an end. If it's finite, then its expansion might behave differently under extreme conditions. Some theories suggest that in the far future, space could collapse back in on itself in a big crunch if the universe is closed and finite. Other models predict an eternal expansion that keeps stretching space forever. There is also the issue of whether space itself is something or just a concept. If the universe is finite, does that mean space is a physical thing with a definite shape? If it's infinite, does that mean space itself has no true structure? Some physicists argue that space is not a substance, but just a relationship between objects. In this view, the question of infinity may not have a straightforward answer because space only exists in relation to the matter within it. Whether the universe is infinite or finite remains an open question. The evidence suggests both possibilities could be true, depending on how space and time behave at the largest scales. Scientists continue to study cosmic background radiation, galaxy distribution, and mathematical models to refine their understanding. The answer may remain just beyond reach, forever hidden by the limits of observation. Dark matter is one of the biggest mysteries in science. Scientists know it exists, but they cannot see or touch it. They only know it is there because of its effect on other objects in space. When they look at galaxies, they see stars moving in ways that do not match the amount of visible matter. The galaxies should fly apart based on what we can see, but they stay together. Something invisible must be holding them in place. That something is called dark matter. The idea of dark matter started almost a century ago. In the 1930s, Swiss astronomer Fritz Zwicky noticed that galaxies in a distant cluster were moving too fast. According to Newton's laws, they should have scattered apart, but they did not. He suggested there was some unseen matter providing extra gravity to hold them together. At the time, few took his idea seriously. Decades later, American astronomer Vera Rubin found similar results when studying the rotation of galaxies. Stars on the edges of galaxies were moving just as fast as those near the center. That was unexpected. If only visible matter existed, the outer stars should have been much slower. Instead, they behaved as if they were in a much larger, unseen mass. Scientists call this unseen mass dark matter. It does not emit, absorb, or reflect light. That makes it impossible to see with telescopes. However, they can detect its presence by measuring its gravitational effects. Galaxies are the best example, but dark matter also affects the way light bends as it travels through space. When light from a distant galaxy passes through a massive object like another galaxy, it bends. This bending is called gravitational lensing. Scientists have found cases where the amount of bending does not match the visible mass. That suggests more mass is present, mass that we cannot see. If dark matter is real, what is it made of? Scientists are still searching for an answer. One possibility is that dark matter is made of tiny particles unlike anything in the standard model of physics. The most popular candidate is the WIMP, or weakly interacting massive particle. WIMPs would have mass, meaning they create gravity, but they would barely interact with normal matter in other ways. That would explain why we cannot see or touch them. If WIMPs exist, they should occasionally collide with normal atoms. Scientists have built underground detectors to try to catch one of these rare interactions. So far, no WIMPs have been found. Another idea is that dark matter is made of axions. Axions are extremely light particles that could fill space like a fluid. Unlike WIMPs, axions would not interact by colliding with atoms. Instead, they might slowly convert into light in the presence of a strong magnetic field. Scientists are using powerful magnets to try to detect these conversions. Like WIMPs, axions remain theoretical. No one has found them yet. There is also a more radical idea. Maybe dark matter is not made of new particles at all. Some scientists believe we may need to change our understanding of gravity. The theory of modified Newtonian dynamics, MN, suggests that gravity behaves differently at very large distances. According to this idea, what we call dark matter might be an effect of gravity changing in ways we do not yet understand. MOND can explain some observations, but it struggles to match the detailed structures of galaxies. So far, dark matter as a particle remains the leading theory. Some scientists wonder if dark matter could be made of something more familiar. Could it be black holes? Primordial black holes, formed in the early universe, might be small enough and numerous enough to explain dark matter. However, if that were true, scientists should see specific gravitational effects that do not appear in their observations. While black holes contribute to dark matter, they do not seem to be the main explanation. Even though dark matter remains unseen, its effects shape the universe. Without it, galaxies might never have formed. In the early universe, normal matter was too hot and energetic to clump together. Dark matter, which does not interact with light, could have acted as a kind of scaffolding. It formed invisible structures first, and normal matter gathered around them, eventually forming galaxies and stars. Computer models of the universe's growth only match observations when dark matter is included. Dark matter also affects cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation provides a snapshot of the universe when it was just 380,000 years old. Small variations in this radiation reveal how matter was distributed. The patterns only make sense if there is more mass than what we can see. Dark matter explains these patterns and helps scientists understand the universe's early days. Efforts to find dark matter continue in different ways. Particle accelerators, like the Large Hadron Collider, smash particles together at high speeds. Some theories suggest that these collisions could produce dark matter particles. If that happens, scientists would see missing energy, as dark matter would escape detection. So far, no clear signs of dark matter have appeared in these experiments. Other searches involve studying the movement of stars and galaxies in more detail. Scientists are mapping the sky with telescopes that can detect faint gravitational lensing effects. By measuring how much dark matter bends light, they hope to learn more about its distribution and properties. Some experiments also look for high-energy signals from space. If dark matter particles collide, they might produce gamma rays, or other detectable signals. Telescopes like the Fermi Gamma Ray Space Telescope are scanning the sky for such signs. One of the biggest questions about dark matter is how it fits into the bigger picture of physics. The Standard Model explains how known particles behave, but it does not include dark matter. If dark matter is a particle, then something must be missing from the Standard Model. This means finding dark matter could lead to new physics, just as past discoveries have expanded our understanding. While dark matter remains elusive, scientists are confident it is real. The evidence is strong, and alternative explanations struggle to match observations. Every new experiment brings the possibility of discovery. Whether it turns out to be WIMPs, axions, modified gravity, or something else entirely, solving the mystery of dark matter will change our understanding of the universe. Dark energy is one of the biggest mysteries in cosmology. Scientists discovered it while studying how the universe expands. In the early 20th century, astronomers thought gravity would eventually slow this expansion. But in the 1990s, observations of distant supernovae showed something unexpected. The universe is not just expanding, it is expanding faster over time. This was a surprise because gravity should pull everything together. Instead, something seems to be pushing everything apart. Scientists call this unknown force dark energy. Dark energy makes up about 68% of the universe. That means most of the universe is something we do not fully understand. The rest consists of dark matter, which is another mystery, and normal matter, which includes stars, planets, and people. Scientists only see dark energy through its effect on the universe's expansion. They do not know what it is made of or where it comes from. One way to think about dark energy is to imagine a balloon. If you blow air into a balloon, it expands. Now imagine that after you stop blowing, the balloon keeps expanding on its own, but at an increasing speed. This is similar to what happens with the universe. The galaxies are like dots on the surface of the balloon, and as the universe expands, these dots move farther apart. But instead of slowing down, the expansion speeds up. The discovery of dark energy came from a study of type Ia supernovae. These are exploding stars that always shine with the same brightness. Because their brightness is predictable, astronomers use them to measure distances in space. In the 1990s, two teams of scientists expected to find that the universe's expansion was slowing. Instead, they found it was accelerating. This meant something had to be driving the expansion. The simplest explanation was that empty space itself had energy. This idea was not new. Albert Einstein had once introduced a similar concept called the cosmological constant. He later abandoned it, but after the discovery of dark energy, scientists revived the idea. The cosmological constant suggests that empty space has a built-in energy that does not change over time. This energy causes space itself to stretch. As more space appears, more of this energy exists, making the expansion continue at an accelerating rate. This explanation fits current observations, but it raises new questions. If empty space has energy, why does it have the amount we observe? Could this energy change in the future? Scientists do not yet have answers. Some researchers believe dark energy is not a constant, but something more dynamic. One idea is called quintessence. This theory suggests dark energy is a field that changes over time. Instead of a fixed amount of energy in empty space, quintessence would evolve, possibly even reversing the acceleration in the far future. If this is true, the fate of the universe could be very different from what scientists predict today. Another idea is that dark energy is a sign that our understanding of gravity is incomplete. Einstein's general relativity explains how gravity works on large scales, but it might not be the full story. Some theories suggest that gravity behaves differently at vast distances. If true, what looks like dark energy might be the result of an unknown property of gravity itself. Astronomers test these ideas by studying how galaxies and clusters of galaxies move. One method involves the cosmic microwave background, the faint glow left over from the Big Bang. This radiation contains subtle patterns that tell us how matter was distributed in the early universe. By comparing these patterns to how the universe looks today, scientists can see the effects of energy over time. Another way to study dark energy is by looking at large-scale structures in the universe. Galaxies are not randomly scattered. They form clusters and long filaments, with huge empty spaces in between. The way these structures grow depends on how the universe expands. If dark energy changes over time, it would affect how these cosmic structures form. Observing them helps scientists test different theories about dark energy. Dark energy also affects the future of the universe. If it remains constant, galaxies will continue moving apart, making the universe colder and emptier over time. If dark energy gets stronger, expansion could speed up so much that galaxies, stars, and even atoms get torn apart in what some scientists call the Big Rip. If dark energy weakens or reverses, gravity could take over again, leading to a collapse called the Big Crunch. One challenge in studying dark energy is that it does not interact with anything directly. Unlike dark matter, which affects galaxies through gravity, dark energy only appears in the universe's expansion. Because of this, scientists rely on indirect methods to study it. They use telescopes to observe distant galaxies, supernovae, and cosmic background radiation. They also create simulations to test different theories and compare them to real data. Future telescopes will provide more information. The Euclid Space Telescope and the Vera C. Rubin Observatory will map billions of galaxies, helping scientists track the effects of dark energy over time. The Nancy Grace Roman Space Telescope, planned for launch later this decade, will also study dark energy in detail. These projects may reveal whether dark energy is a constant force or something that evolves. Some scientists explore even stranger ideas. One possibility is that our universe is part of a larger multiverse. In this view, different regions of space could have different amounts of dark energy. Another idea is that dark energy could be linked to quantum mechanics, the rules that govern the smallest particles. In quantum physics, empty space is not truly empty. It is full of tiny particles that pop in and out of existence. Some researchers wonder if dark energy is connected to this quantum activity. Despite decades of research, dark energy remains one of the biggest puzzles in physics. It challenges our understanding of the universe at the most fundamental level. Whether it is a constant force, a changing field, or a sign that gravity needs revision, solving this mystery will reshape our view of the cosmos. Scientists continue to gather data, hoping that the next discovery will bring them closer to an answer. Some scientists think parallel universes might exist. The idea comes from physics and cosmology, especially from quantum mechanics and the theory of the multiverse. A parallel universe would be another reality, separate from ours, but possibly similar in some ways. The big question is whether these universes are real or just ideas that help explain things we don't fully understand. One reason scientists consider parallel universes is quantum mechanics. This branch of physics describes how tiny particles, like electrons and photons, behave. The famous double-slit experiment shows that particles act like both waves and particles at the same time. When scientists observe them, the particles seem to choose a state. Some interpretations suggest that every possible choice actually happens, but in different universes. This idea is called the many worlds interpretation. If it's correct, then every decision you make creates a new universe where the other choice plays out. In one universe, you decide to take a new job. In another, you don't. Both versions exist, but you can only experience one. Another reason scientists think about parallel universes comes from cosmology. The universe began with the Big Bang, about 13.8 billion years ago. Since then, it has expanded. Some theories suggest that space might keep expanding forever, creating an infinite number of regions. If space is infinite, then somewhere, far beyond what we can see, there could be another version of Earth, nearly identical to ours, with people who look just like us. This idea comes from probability. If you roll a die enough times, eventually you will get the same number sequences again. If the universe is truly infinite, then patterns of particles might repeat, creating another version of you somewhere else. There is also the theory of cosmic inflation. This idea explains how the universe expanded extremely fast just after the Big Bang. Some versions of this theory suggest that inflation never completely stopped. Instead, different regions of space could have continued expanding at different rates, creating bubble universes. Each bubble could be its own universe with its own physical laws. In some, gravity might be stronger. In others, atoms might not exist at all. These universes might be completely separate, meaning we could never reach or observe them. Scientists have tried to find evidence for parallel universes, but so far, nothing confirms they exist. One idea is to look at the cosmic microwave background, which is the leftover radiation from the Big Bang. Some researchers think that if another universe had collided with ours in the past, it might have left a mark. So far, no clear evidence of such a collision has been found. Others have suggested that strange quantum effects might be signs of parallel worlds interacting with ours, but there's no proof yet. Some theories go beyond physics and suggest that parallel universes could explain strange experiences. Some people claim to have memories of events that never happened in this reality. This is sometimes called the Mandela effect. For example, many people remember Nelson Mandela dying in prison in the 1980s, even though he was released and later became president of South Africa. Some think these false memories could come from slipping between parallel universes, though psychologists usually explain them as tricks of the brain. Popular culture loves the idea of parallel universes. Books, movies, and TV shows often explore worlds where history turned out differently. What if the Nazis won World War II? What if humans never evolved? These stories make the idea seem exciting and dramatic, but real science is more cautious. Just because something is a good story doesn't mean it's real. If parallel universes exist, would we ever be able to visit them? Right now, there's no known way. Even if another universe were just next to ours, we don't know how to cross into it. Some theories suggest that black holes might be gateways, but there's no evidence for that either. Wormholes, which are hypothetical tunnels through space-time, are another idea. If they exist, they might connect different universes, but no one has ever found one. The question of parallel universes is tied to a bigger mystery: the true nature of reality. Scientists don't fully understand why the universe exists the way it does. Some think there could be deeper laws of physics that we haven't discovered yet. If parallel universes are real, they might help explain why our universe has the conditions necessary for life. In some universes, the laws of physics might be slightly different, making life impossible. If there are infinite universes, then it's not surprising that at least one of them allows for human existence. Some physicists argue that the idea of parallel universes can never be tested, which means it might not be real science. A scientific theory needs to make predictions that can be tested with experiments or observations. If parallel universes exist but can never be detected, then some argue that the idea is more philosophy than physics. Others disagree and think that future discoveries might change our understanding. Even though there is no proof of parallel universes, the idea remains a serious topic in physics. It connects to quantum mechanics, cosmology, and the nature of reality itself. As scientists learn more about the universe, they might find clues that point to other worlds. Until then, the idea remains a fascinating possibility rather than a confirmed fact. Scientists have long wondered if the laws of physics are the same everywhere in the universe. On Earth, we rely on physical laws to explain everything from how apples fall from trees to how rockets launch into space. These laws describe how matter and energy behave, and they help us predict the future. But what if, in some distant part of the universe, the rules are different? What if gravity works in a new way or atoms interact in a manner we've never seen before? To answer this question, we must first understand what we mean by laws of physics. These are the fundamental rules that govern the universe. They include things like Newton's laws of motion, Einstein's theory of relativity, and the laws of thermodynamics. These laws work together to explain everything we see around us. For example, the law of gravity tells us why planets orbit the sun, while the laws of electromagnetism explain how light moves through space. So far, every experiment we've conducted on Earth and in space has shown that these laws hold true. Scientists have studied the behavior of atoms, the movement of galaxies, and the interactions of subatomic particles. No matter where they look, they see the same rules at work. This consistency has led many to believe that the laws of physics are universal. However, there are reasons to think this might not be the whole story. One clue comes from the study of the fundamental constants of nature. These are numbers that appear in the equations of physics and determine how strong forces like gravity and electromagnetism are. One example is the speed of light, which is about 186,000 miles per second. Another is the fine structure constant, which controls how atoms absorb and emit light. If these numbers changed, even slightly, the universe would look very different. Atoms might not form, stars might not shine, and life as we know it might be impossible. Scientists have tried to measure whether these constants are the same everywhere in the universe. They've looked at light from distant galaxies to see if the fine structure constant has changed over billions of years. Some studies suggest tiny variations, but the results are not yet conclusive. If these measurements are correct, it could mean that the laws of physics are not as fixed as we thought. Another possible clue comes from the idea of extra dimensions. In our daily lives, we experience 3 dimensions of space: length, width, and height, plus time as the 4th dimension. But some theories, like string theory, suggest that the universe has more dimensions that we can't see. These extra dimensions could change how forces like gravity behave. If gravity acts differently in another part of the universe because of hidden dimensions, then the laws of physics might not be the same everywhere. The idea of different physical laws becomes even more interesting when we consider the multiverse hypothesis. Some scientists believe that our universe is just one of many. If other universes exist, they might have completely different rules. Gravity might be stronger or weaker, or atoms might not exist at all. In some universes, stars might never form, while in others, black holes might dominate everything. Even within our own universe, extreme environments might reveal new physics. Black holes are one example. The laws of physics, as we understand them, break down at the center of a black hole. This means we don't yet have a complete picture of how the universe works in the most extreme conditions. Similarly, the conditions during the first moments after the Big Bang were so hot and dense that our current theories struggle to explain them. If we could understand physics in these extreme settings, we might find that different laws apply in different places. There is also the question of whether intelligent life could exist in a universe with different laws. On Earth, the chemistry of life depends on carbon, water, and the ability of atoms to form complex molecules. But what if the laws of physics were different? Could life exist in a universe where gravity is much stronger, or where light moves at a different speed? Some scientists speculate that alternative forms of life might be possible under different rules. However, it's also possible that our universe is one of the few where life can exist at all. Some researchers look for evidence of changing physical laws by studying cosmic structures on the largest scales. They examine how galaxies cluster together and how the universe expands over time. If the laws of physics vary from place to place, we might see subtle differences in how galaxies form or how light from distant stars behaves. So far, most observations suggest that the same rules apply everywhere, but new discoveries could change this view. Another approach involves experiments in high-energy physics. Scientists use particle accelerators to recreate conditions similar to those found in the early universe. By smashing particles together at high speeds, they test whether the known laws of physics hold up in extreme conditions. These experiments have already revealed unexpected behaviors, such as particles appearing to change from one type to another. If researchers discover new forces or particles, it could hint at deeper physical laws that only become apparent under special conditions. The search for different physical laws also leads to philosophical questions. If the laws of physics are the same everywhere, does that mean they were designed to be that way? If they change over time or across space, what determines how they change? Some theories suggest that the laws of physics emerge from deeper principles we don't yet understand. Others propose that physical laws are simply random and that we happen to live in a universe where the right conditions exist for galaxies, stars, and life. While most evidence suggests that the laws of physics are constant throughout our universe, scientists remain open to the possibility that they might change under certain conditions or in other regions of space. As we continue to explore, we may discover new aspects of reality that challenge our understanding of the cosmos. The universe is vast and full of mysteries, and our search for its fundamental truths is far from over. A black hole is one of the most mysterious objects in the universe. It forms when a massive star collapses under its own gravity. This collapse creates a region in space where gravity is so strong that nothing can escape, not even light. The boundary of a black hole is called the event horizon. Once something crosses this invisible line, it is lost forever. The idea of falling into a black hole is both fascinating and terrifying. What happens inside remains one of the biggest questions in physics. Imagine an astronaut approaching a black hole. As they get closer, they would feel the pull of gravity getting stronger. If they were falling feet first, the gravity at their feet would be much stronger than the gravity at their head. This difference in force would stretch them out like a piece of spaghetti. Scientists call this spaghettification. If the black hole were small, the astronaut would be torn apart before even reaching the event horizon. But if the black hole were massive, they might cross the event horizon without feeling anything unusual at first. Once inside, the astronaut would be in a place where space and time behave differently. In normal space, time moves at a steady pace. Inside a black hole, time slows down and may even stop at the center. The closer they get to the center, the stronger gravity becomes. No force in the universe can pull them back. The center of the black hole is called the singularity. This is a point where all the mass of the black hole is concentrated. The laws of physics break down here. Gravity is so strong that it bends space and time to an infinite degree. Scientists do not know exactly what happens at the singularity because current physics cannot describe it. Some theories suggest that the singularity could be a gateway to another universe. Others suggest that the laws of physics simply stop making sense at that point. If someone outside the black hole were watching the astronaut fall in, they would see something strange. As the astronaut approaches the event horizon, they would appear to slow down. Their movements would get slower and slower until they seemed frozen in place just outside the black hole. This happens because gravity stretches time. The light coming from the astronaut would also become redder and dimmer until it fades away completely. This is called gravitational redshift. In reality, the astronaut would continue to fall, but no one outside the black hole would ever see them cross the event horizon. Once inside, the astronaut's fate depends on the type of black hole. In a smaller black hole, gravity changes sharply over short distances. The astronaut would be stretched and torn apart before reaching the singularity. But in a supermassive black hole, which is millions or billions of times the mass of the Sun, gravity changes more gradually. The astronaut might survive longer and even float inside for a while before being crushed by the singularity. One of the biggest mysteries is whether anything that falls into a black hole is truly lost. According to classical physics, once something crosses the event horizon, it can never escape. But quantum physics suggests that information cannot be destroyed. This leads to what scientists call the black hole information paradox. Some theories suggest that information is stored at the event horizon. Others propose that black holes slowly evaporate over time, releasing information back into the universe. This process, known as Hawking radiation, suggests that black holes are not permanent. Over billions of years, they could shrink and eventually disappear. If black holes evaporate, what happens to everything that fell inside? This is still unknown. Some scientists think that the information is released in a scrambled form as the black hole evaporates. Others believe it is stored in a way we do not yet understand. There is also a theory that when a black hole collapses completely, it could create a new universe on the other side. If true, this would mean that every black hole could be the seed of a new cosmos. Inside a black hole, space and time do not work the way we experience them. In everyday life, we think of space as a three-dimensional area where things move and time as something that flows forward. In a black hole, these roles change. Time moves inward toward the singularity like a one-way road. No matter what an object does inside, it must move toward the center. Even if the astronaut had a powerful spaceship, they could not turn around. The singularity is not just a place, but a moment in time that cannot be avoided. Some scientists have explored the idea that black holes could be wormholes. A wormhole is a theoretical tunnel that connects two different points in space and time. If black holes contain wormholes, then falling into one might not mean destruction. Instead, it could lead to another part of the universe or even a completely different universe. However, no evidence for wormholes has been found yet. There are different types of black holes, and each might behave differently inside. Stellar mass black holes form from collapsing stars and are relatively small. Supermassive black holes exist at the centers of galaxies and are millions to billions of times heavier than the Sun. There is also a possibility of primordial black holes, which may have formed in the early universe. Some theories even suggest microscopic black holes could exist, though they have not been observed. The study of black holes has changed our understanding of the universe. They challenge the way we think about space, time, and physics itself. Scientists continue to search for answers using advanced telescopes and mathematical models. The more we learn about black holes, the more questions arise. Understanding what happens inside them could reveal new laws of physics and give us deeper insights into the nature of reality. A white hole is a theoretical object in space that is the opposite of a black hole. While a black hole pulls in everything that comes near it, a white hole pushes everything away. Nothing can enter a white hole, just like nothing can escape a black hole. Scientists first thought of white holes when studying black holes and how they affect space and time. Black holes form when a massive star collapses under its own gravity. This creates a region in space where gravity is so strong that nothing can escape, not even light. A white hole, if it exists, would work in reverse. Instead of pulling matter in, it would constantly eject matter and energy. It would also prevent anything from entering. If someone tried to fly a spaceship toward a white hole, they would be pushed away by a powerful force before they could get close. Mathematicians discovered white holes while studying the equations that describe black holes. When they solved these equations, they found that they allowed for a second type of object that behaves in the opposite way. This led to the idea that white holes might exist somewhere in the universe. However, no one has ever observed one. The equations allow them to exist, but that does not mean they are real. Scientists have debated whether white holes could form naturally. One idea is that they might be the other end of a black hole. In this theory, when something falls into a black hole, it might come out of a white hole somewhere else in the universe. This would make a black hole and a white hole part of the same system, connected by a tunnel called a wormhole. If this were true, then black holes would not destroy information, but instead send it to another place in the universe. However, there is no proof that this happens. Another idea is that white holes might be what black holes become when they die. Black holes slowly lose energy over time through a process called Hawking radiation. Some scientists think that when a black hole shrinks to a very small size, it could turn into a white hole and explode, releasing all the matter and energy it had absorbed. If this happens, then white holes might be very short-lived, which could explain why no one has seen one. White holes would look very different from black holes. A black hole is invisible because it traps all light inside. Scientists can only detect black holes by looking at how they affect nearby stars and gas clouds. A white hole, on the other hand, would be extremely bright. It would constantly emit energy and matter in all directions. It might look like a star, but behave in a way that no normal star does. It would push everything away instead of pulling things toward it. If white holes exist, they could help answer some big questions about the universe. Scientists still do not fully understand what happens inside black holes. If black holes and white holes are connected, studying white holes could reveal new information about the nature of space and time. White holes might also help explain what happened at the beginning of the universe. Some researchers think that the Big Bang, which created the universe, might have been similar to a white hole explosion. This idea suggests that the universe itself might be the result of a massive white hole appearing from nothing. There are challenges to the idea of white holes. One big problem is that they seem impossible to create. Black holes form naturally when stars collapse, but there is no known process that could create a white hole. Some scientists think that if white holes ever existed, they would have been unstable and disappeared quickly. Others believe that if white holes exist, they might be hidden in places we have not looked yet. They could be in distant galaxies or in regions of space where we do not have the ability to observe them. Another challenge is that white holes do not fit well with what scientists know about the universe. The laws of physics say that things tend to move toward disorder over time. This idea, called entropy, suggests that white holes should not exist. A white hole would be a region of perfect order in the universe, which goes against everything scientists understand about how things work. This makes many experts skeptical that white holes are real. Some researchers have tried to find white holes by looking for unusual bursts of energy in space. One possibility is that white holes might look like gamma-ray bursts, which are extremely powerful flashes of energy that come from distant galaxies. These bursts happen suddenly and last only a few seconds. Scientists do not fully understand what causes them, so some have suggested that they could be white holes appearing and disappearing quickly. However, there is no direct evidence to support this idea. There are also ideas about how white holes might affect time. Some theories suggest that time might flow differently near a white hole, just as it does near a black hole. In a black hole, time slows down as you get closer to the center. If white holes exist, they might have the opposite effect, causing time to speed up near them. This could create strange effects where time moves faster in some parts of the universe than in others. However, without real observations, this is just speculation. Some science fiction stories explore the idea of white holes as portals to other parts of the universe. If a white hole is connected to a black hole by a wormhole, then it could be used as a shortcut through space. A spaceship could enter a black hole and come out of a white hole somewhere else. This would allow travel between distant parts of the universe much faster than the speed of light. However, most scientists think this is unlikely. Even if white holes exist, the forces involved would probably destroy anything that tried to pass through. Although no one has ever seen a white hole, some scientists continue to study them because they challenge what we know about physics. If white holes do not exist, then scientists need to explain why the equations that describe them do not match reality. If they do exist, then they could reveal new insights into the nature of space, time, and gravity. Future telescopes and experiments might provide more clues. For now, white holes remain an interesting but unproven idea. Scientists have found plenty of black holes, but no white holes. Until there is real evidence, white holes will remain a mystery. Time travel is one of the most fascinating ideas in science. It has appeared in books, movies, and TV shows for decades. People dream of going back to change mistakes or jumping forward to see the future. But is it actually possible? Scientists take this question seriously. Time is not as simple as it seems. We experience it as a steady flow from past to present to future, but physics tells a different story. Einstein's theory of relativity changed how we understand time. It showed that time and space are connected. They form what scientists call spacetime. Objects with mass bend spacetime, and the stronger the gravity, the slower time moves. We see this effect in real life. Satellites orbiting Earth experience time slightly faster than people on the ground. Their clocks tick a tiny bit ahead because Earth's gravity is weaker in space. This difference is small, but it proves that time does not move at the same speed everywhere. This idea opens the door to time travel. If time can slow down, could it also be controlled? Scientists have explored different possibilities. One of them is speed. The faster you move, the slower time is for you. This is called time dilation. Astronauts on the International Space Station move at over 17,000 miles per hour. Their time moves slightly slower compared to people on Earth. If they stayed in space for years, they would age less than people on the ground. This means they are technically traveling into the future, just by tiny amounts. If someone could travel near the speed of light, time dilation would be extreme. A person on a spaceship moving at 99% of the speed of light would age much slower than someone on Earth. If they left for a year and came back, decades might have passed on Earth. This is not just a theory. Scientists have tested it with particles. High-speed particles experience time slower than slow-moving ones. Black holes create another possibility. They have enormous gravity. If someone got close to a black hole without falling in, time would slow down for them. They could orbit the black hole for a few years, but when they returned, much more time would have passed on Earth. These examples show how traveling to the future is possible, at least in theory. But what about the past? Going backward is much harder. One idea involves wormholes. These are shortcuts in space-time. Imagine space as a flat sheet of paper. If you fold the paper and punch a hole through it, you create a shortcut between 2 points. A wormhole could do something similar for time. If a wormhole connected 2 different points in time, someone could step through it and arrive in the past. But wormholes, if they exist, would be unstable. They might collapse before anything could pass through. Scientists also think huge amounts of negative energy would be needed to keep them open, something we don't know how to create. Another idea comes from theoretical physicist Kurt Gödel. He showed that if the universe rotated, it might be possible to travel in a loop and end up in the past. But observations show that our universe does not rotate in this way. There is also the concept of closed time-like curves. These are paths in space-time that loop back on themselves. If such a path existed, a person could follow it and return to an earlier moment. Some equations suggest this could happen around rotating black holes, but there is no proof that such paths exist in reality. Even if traveling to the past were possible, it would create paradoxes. The most famous one is the grandfather paradox. Imagine someone goes back in time and stops their grandfather from meeting their grandmother. That means they were never born. But if they were never born, how did they travel back in time? Some scientists think nature might prevent paradoxes. The Novikov self-consistency principle suggests that events in time correct themselves. If you went back in time, you would not be able to change anything in a way that creates a contradiction. For example, if you tried to stop your grandfather from meeting your grandmother, something would always stop you. Others suggest parallel timelines. If you change the past, you would create a new timeline instead of changing your own. In this case, you could travel to the past, but your original timeline would remain unchanged. There is also the possibility that time travel is simply impossible. Some scientists argue that the laws of physics do not allow it. Stephen Hawking suggested a chronology protection conjecture. He believed that physics prevents time travel because it would create too many inconsistencies. The question of time travel is still open. Traveling forward in time is possible through speed and gravity, but going back remains uncertain. Scientists continue to explore the possibilities, but for now, time remains a one-way road. The universe is constantly changing. Galaxies move farther apart, stars are born and die, and black holes grow in mass. But what will happen in the long run? Scientists believe the universe has a fate, just like everything else. To understand what might happen, we have to look at the forces at work and the evidence we have so far. The biggest clue comes from how the universe expands. In the early 20th century, astronomers believed the universe was static. That changed when Edwin Hubble discovered that galaxies are moving away from us. The farther a galaxy is, the faster it moves. This showed that the universe is expanding. Scientists thought gravity would slow this expansion over time. If there was enough mass, gravity might even pull everything back together in a big crunch. If there wasn't enough mass, expansion might continue forever but slow down. That view changed in 1998. Astronomers studying distant supernovae found something shocking. Instead of slowing down, the universe was expanding faster. This meant an unknown force was pushing galaxies apart. Scientists called this force dark energy. Unlike gravity, which pulls things together, dark energy makes space itself expand. It acts everywhere and increases with time. About 70% of the universe is dark energy, while dark matter and regular matter make up the rest. Dark energy changes our understanding of the universe's future. If it stays the same, expansion will continue accelerating. Galaxies will move farther apart. Over billions of years, they will disappear from view. The night sky will go dark except for our own galaxy and its closest neighbors. Stars will still form, but over time there will be less gas to make them. The last stars will burn out, leaving behind cold remnants like black holes, neutron stars, and white dwarfs. This scenario is called the Big Freeze. As the universe expands, it cools. With no more energy sources, temperatures will drop close to absolute zero. Even black holes will evaporate due to a slow process called Hawking radiation. Over an unimaginable time span, all structures will break down. Only faint, scattered particles will remain in a vast, empty space. Some scientists think dark energy might change over time. If it grows stronger, expansion could speed up until it rips apart galaxies, solar systems, and even atoms. This idea is called the Big Rip. Everything would dissolve into fundamental particles. This would happen far sooner than the Big Freeze. Instead of trillions of years, it could unfold in just a few billion years. There is also the possibility that dark energy could reverse. Instead of pushing things apart, it might turn attractive. If that happens, the universe could collapse in a big crunch. Gravity would overwhelm expansion, pulling everything back together. Galaxies would merge, then stars, then atoms. The universe would shrink into a hot, dense state, possibly similar to how it began. Some scientists think this cycle could repeat in a big bounce, where the universe expands and contracts forever. These are the main possibilities, but there is much we don't know. Dark energy is still a mystery. Scientists can't explain what it is or why it behaves the way it does. Observations of galaxies and cosmic background radiation give us clues, but they don't provide a final answer. Another factor is black holes. Over time, black holes consume matter and grow larger. In a far future, they might be the only structures left. If something allows them to survive indefinitely, the last remnants of the universe might exist as massive black holes. But if Hawking radiation continues as expected, even these giants will eventually fade away. Scientists also consider the possibility that the universe is part of a larger structure. Some theories suggest our universe could leak into another reality, or that quantum fluctuations might trigger a new Big Bang. If true, what seems like an ending might just be a transformation into something else. For now, the best evidence suggests the Big Freeze. The universe is expanding too fast for gravity to stop it. Stars will burn out, matter will decay, and eventually space will become empty. It is a slow process, taking trillions of years, but the direction seems clear. Understanding the fate of the universe helps us understand our place in it. We exist in a brief, golden era where stars shine and life can form. This will not last forever. The universe was once a hot, dense fireball, and in time it will become a cold, empty void. What happens in between is the story of cosmic evolution, driven by forces we are only beginning to understand. Scientists have searched for alien life for decades. Some believe we may have already seen hints, while others argue we have no solid evidence. The universe is vast, with billions of galaxies, each containing billions of stars and even more planets. The odds suggest life exists somewhere else. The challenge is finding it and making contact. Radio signals are one way scientists listen for alien life. Programs like SETI, the Search for Extraterrestrial Intelligence, scan the sky for unusual signals. Most signals come from stars, planets, or human-made satellites, but some remain unexplained. In 1977, astronomer Jerry Eman detected the famous WOW signal, a strong, unusual burst of radio waves. It lasted 72 seconds and never repeated. Some speculate it was a sign of intelligent life, but without a repeat signal, scientists can't confirm the source. Another way to search is by looking for biosignatures, chemical signs of life in a planet's atmosphere. Telescopes like the James Webb Space Telescope can analyze distant planets, searching for gases like oxygen or methane, which could indicate living organisms. In 2020, scientists detected phosphine in the atmosphere of Venus. On Earth, phosphine is mostly produced by bacteria. The discovery sparked debate. Some thought it was evidence of microbial life. Others argued it was a mistake in data collection. Follow-up studies found no clear answer, leaving the question open. Mars has been a focus in the search for alien life. NASA's rovers, like Perseverance, explore the planet's surface, drilling into rocks and searching for ancient microbial fossils. Scientists believe Mars once had liquid water, a key ingredient for life. In 1996, researchers found a meteorite from Mars containing structures that looked like fossilized bacteria. Many scientists doubted the claim, suggesting the shapes were formed by chemical processes instead. Even so, Mars remains one of the best places to look for past or present life. Some scientists search for alien life by looking at extreme environments on Earth. Life thrives in deep-sea vents, under Antarctica's ice, and in acidic lakes. These organisms, called extremophiles, suggest that life could exist in harsh places like Jupiter's moon Europa or Saturn's moon Enceladus. Both moons have oceans beneath thick ice crusts. Scientists believe these oceans may have hydrothermal vents, like those on Earth, which could provide the energy needed for life. The search for intelligent alien life raises another question. If they exist, why haven't we heard from them? This question is known as the Fermi paradox. Some possible explanations include the idea that intelligent civilizations destroy themselves before they can communicate. Others suggest aliens use technology we don't yet understand. They may also be avoiding us on purpose, watching but choosing not to interfere. If we did receive a message from an alien civilization, scientists would need to verify it. They would check for patterns that rule out natural sources. Once confirmed, the challenge would be deciding how to respond. Governments and scientific organizations have debated this. Some believe we should send a message back immediately, while others warn that alerting advanced aliens to our existence could be dangerous. Humanity has already sent messages into space. In 1974, scientists broadcast the Arecibo message, a binary encoded signal aimed at a star cluster 25,000 light-years away. The Voyager probes, launched in 1977, carry golden records with sounds and images from Earth, designed to introduce our world to any civilization that finds them. These efforts are symbolic, as the chances of a response in our lifetime are low. A direct encounter with aliens is another possibility. If an advanced civilization reached Earth, the outcome would depend on their intentions. Some scientists believe a peaceful meeting is possible, comparing it to human encounters with new cultures. Others warn that history shows more powerful civilizations often dominate weaker ones. If aliens view us as insignificant or as a resource, the consequences could be serious. Despite the unknowns, the search continues. New telescopes will scan more exoplanets for life signs. Rovers will dig deeper into Mars. Missions to Europa and Enceladus may sample their oceans. If alien life exists, the question is not just where, but when we will find it. Are we alone in the universe? The question has fascinated humans for centuries. Scientists search the skies for signs of life beyond Earth, but so far, we haven't found clear evidence. The universe is vast, with billions of galaxies, each containing billions of stars and planets. The odds suggest that life should exist somewhere else, yet we have no proof. Astronomers look for planets in the habitable zone, where conditions might support liquid water. Water is essential for life as we know it. NASA's Kepler Space Telescope identified thousands of exoplanets, some of which seem similar to Earth. The James Webb Space Telescope is now studying their atmospheres, searching for chemical signatures that could suggest life. Microbial life is the simplest form of life and might be the most common. On Earth, microbes thrive in extreme environments, boiling hot springs, deep-sea vents, and even frozen tundras. If microbes can survive in such harsh conditions here, they might also exist on Mars, Europa, or Enceladus. Mars once had rivers and lakes, and scientists believe it may have supported microbial life in the past. The Perseverance rover is currently looking for ancient signs of life in Jezero crater. Europa, one of Jupiter's moons, has an icy shell covering a vast ocean. Tidal forces from Jupiter's gravity keep the ocean warm beneath the ice. Some scientists believe hydrothermal vents on Europa's ocean floor could support life, just as similar vents do in Earth's deep oceans. NASA plans to send the Europa Clipper mission to investigate further. Saturn's moon Enceladus also has a subsurface ocean. The Cassini spacecraft detected plumes of water vapor shooting into space. These plumes contain organic molecules, which are building blocks of life. Future missions may fly through the plumes and analyze their contents for signs of microbes. Beyond our solar system, astronomers use powerful telescopes to scan distant planets. They search for biosignatures, gases like oxygen, methane, or carbon dioxide that could indicate life. Earth's atmosphere contains these gases because of biological activity. If we detect similar patterns elsewhere, it could suggest life. The search for intelligent life takes a different approach. The SETI Institute uses radio telescopes to listen for signals from other civilizations. The idea is simple. If intelligent beings exist, they might try to communicate. Radio waves travel well through space, so SETI focuses on detecting unnatural patterns in radio signals. So far, they have found nothing conclusive. One famous event in the search for alien signals was the WOW signal, detected in 1977. It was a strong radio signal that lasted 72 seconds and came from deep space. Scientists could not identify a natural source, leading to speculation that it was an artificial transmission. Despite repeated efforts, the signal was never detected again, leaving its origin a mystery. Another possibility is that intelligent life is rare or short-lived. Civilizations may develop technology, but destroy themselves before achieving interstellar communication. Nuclear war, climate change, or artificial intelligence could pose existential threats. If most civilizations self-destruct, the galaxy might be full of planets where life once existed but is now gone. Some scientists propose the idea of a great filter. This is a stage in evolution or civilization that is extremely difficult to pass. If life is common, but intelligent life is rare, the great filter could be the step from simple cells to complex organisms. If many civilizations arise but never reach space exploration, the great filter could be self-destruction. We do not know if humanity has already passed this barrier or if it still lies ahead. The Fermi paradox highlights the contradiction between the high probability of extraterrestrial life and the lack of evidence. If advanced civilizations exist, why haven't we seen them? One explanation is that they do not want to be found. Some argue that broadcasting our presence to the universe could be dangerous. If a highly advanced civilization is out there, its intentions are unknown. Stephen Hawking warned that encountering an alien civilization could be like Native Americans meeting European explorers, an event that did not end well for the less advanced society. Another theory suggests that civilizations avoid contact to prevent interference. A concept called the zoo hypothesis proposes that aliens know about us but choose to observe rather than interact. They might see us as too primitive to engage with. If an advanced species has been watching Earth, they could be waiting for us to reach a certain level of development before revealing themselves. Some believe we are looking in the wrong way. Instead of searching for radio signals, we might need to rethink how advanced civilizations communicate. They could use quantum communication, neutrinos, or even signals encoded in gravitational waves. Our current technology might not be capable of detecting their methods. There is also the possibility that extraterrestrial life exists but is unrecognizable. Life on Earth is carbon-based, but other forms of life might be based on silicon or other unknown chemistry. Some exoplanets have conditions vastly different from Earth's, and life there might not rely on water or oxygen. If we only search for life that resembles our own, we might overlook alien organisms. Another idea is that intelligent civilizations might be digital. Instead of biological beings, advanced life could exist as artificial intelligence. If an advanced species uploaded its consciousness into machines, it might not need planets, water, or oxygen. A digital civilization could travel through space more efficiently, using minimal resources. Some people claim to have seen UFOs, which they believe are evidence of alien visitors. Governments, including the US, have released reports on unexplained aerial phenomena. While most sightings have natural explanations, some remain unidentified. If aliens were visiting Earth, their technology would be far beyond ours. The question remains, if they are here, why do they not make contact in an undeniable way? The search for extraterrestrial life is one of the biggest scientific endeavors. Scientists continue to explore, using telescopes, rovers, and radio signals. Missions to Mars, Europa, and beyond may eventually provide an answer. Whether life is rare or common, the answer will change our understanding of the universe. Life as we know it is based on carbon, water, and DNA. Every organism on Earth, from the smallest bacteria to the largest whale, shares these basic building blocks. But the universe is vast, and there is no reason to believe that life elsewhere must follow the same rules. If life exists on other planets, moons, or even in interstellar space, it may take forms we can't yet imagine. Scientists use Earth's life as a guide when searching for extraterrestrial organisms, but this approach has limitations. It assumes that life needs water, oxygen, and sunlight. While these ingredients sustain most life on Earth, some organisms survive in extreme environments, challenging our ideas about what is necessary. Microbes, called extremophiles, thrive in boiling hot springs, frozen tundras, deep-sea trenches, and even acidic lakes. Some live without sunlight, using chemical reactions instead of photosynthesis. Others survive in the vacuum of space, enduring radiation and extreme temperatures. These creatures show that life can be far more adaptable than we once thought. Consider a world where silicon, not carbon, is the foundation of life. Silicon shares some chemical properties with carbon, allowing it to form complex molecules. While carbon-based life relies on organic molecules, silicon-based life could use different structures to store information, process energy, and reproduce. Instead of water, it might use liquid methane or ammonia as a solvent. This is not just science fiction. Some researchers believe that Titan, Saturn's largest moon, could host such organisms. Titan has lakes of liquid methane and an atmosphere rich in organic molecules. If life exists there, it may be unlike anything found on Earth. Another possibility is plasma-based life, existing in stars or interstellar space. Traditional life depends on solid or liquid matter, but plasma organisms could form from charged particles in extreme environments. The idea may sound far-fetched, but some scientists have suggested that complex structures could emerge in plasma clouds, maintaining themselves and evolving over time. These beings would not need planets or atmospheres. Instead, they could drift through space, feeding on radiation and magnetic fields. Life could also be based on exotic forms of chemistry that do not exist naturally on Earth. Some theories propose that life might rely on quantum effects, using the strange behavior of subatomic particles to store and process information. In this scenario, intelligence might arise in forms we cannot see or measure with current technology. Such beings could exist in ways that defy our understanding of biology, perhaps as networks of particles interacting across vast distances. There is also the possibility of machine-based life. Humans have built computers and artificial intelligence, but natural processes could lead to the formation of self-replicating machines on other worlds. If an alien civilization once created advanced robotic systems, these machines might continue evolving long after their creators vanished. Unlike biological organisms, they would not need food or water. They could adapt to harsh conditions, survive deep space travel, and spread across the galaxy. These entities would not resemble traditional life, but they could be conscious, intelligent, and capable of independent thought. Life forms could also be massive, stretching across entire planets or even star systems. On Earth, single organisms like aspen trees can cover vast areas, connected through underground root systems. An alien version could extend for thousands of miles, sharing a single mind across an entire landscape. Some scientists have speculated about life on gas giants like Jupiter, where floating organisms might exist in the thick atmosphere, feeding on chemical reactions in the clouds. These creatures could grow to enormous sizes, with vast colonies of microbes or even intelligent beings living within them. Another extreme form of life could exist in neutron stars or black holes. The intense gravity and radiation of these environments would destroy Earth-based organisms instantly. But physics allows for the possibility of exotic matter with strange properties. Some theorists have suggested that life could emerge from complex patterns of energy within these extreme conditions. If true, such beings would be completely beyond our ability to detect or communicate with using conventional methods. Even more speculative is the idea that life could exist outside the physical universe as we understand it. Some physicists believe that higher dimensions might exist beyond our three-dimensional world. If so, beings could inhabit these dimensions, interacting with our reality in ways we cannot perceive. These entities might not experience time and space as we do. Their existence could be fleeting from our perspective, but eternal from theirs. If we ever encounter extraterrestrial life, it may not resemble anything we expect. Our attempts to define life are shaped by what we know, but the universe operates on scales and principles that go beyond human experience. Some life forms may use unknown forms of chemistry, while others may exist as pure energy or even as self-aware information structures. The search for life requires an open mind and a willingness to rethink what it means to be alive. The shape of the universe is one of the biggest questions in cosmology. Scientists try to figure it out using physics, mathematics, and observations of space. The universe might seem like an endless void, but it has a structure that follows the laws of physics. Understanding its shape helps us know whether it will expand forever, collapse on itself, or do something else entirely. To study the shape of the universe, scientists use a concept called curvature. Space can be flat, like an infinite sheet of paper. It can be curved like the surface of a sphere, or it can be curved like a saddle, bending outward. Each of these shapes affects how light travels, how galaxies move, and what will happen in the distant future. One way to test this is by looking at cosmic microwave background radiation. This is leftover light from the Big Bang. Scientists analyze patterns in this light to determine the curvature of space. The current evidence suggests that the universe is very close to flat. That means, on the largest scales, space doesn't curve in on itself or bend outward. But the measurements have limits. Even if the universe appears flat to us, it could still curve in ways we haven't detected yet. If the universe is flat, it means it stretches on forever. This is hard to imagine. Our everyday experiences involve shapes with edges or boundaries. But a truly flat universe would have no edge. It would just continue, with galaxies scattered endlessly. If this is correct, then space will keep expanding forever, and the universe will never collapse. If the universe is curved like a sphere, it means space bends back on itself. In this case, if you traveled far enough in one direction, you might eventually end up back where you started. This would mean the universe is finite, though it has no actual boundary. It would be like the surface of Earth. You can keep moving without hitting an edge, but the area itself is limited. A spherical universe would eventually stop expanding and contract back in a process called the Big Crunch. If the universe has a saddle shape, it means space curves outward in all directions. This kind of universe would also be infinite, but it would expand forever at an increasing rate. In this case, galaxies would keep moving apart and space would stretch endlessly. One way scientists test this is by measuring how light bends around massive objects. When light passes by a galaxy, its path changes due to gravity. If space is curved, the way light moves will reveal that curvature. So far, observations suggest the universe has no large-scale curvature, meaning it is either perfectly flat or so large that its curvature is too small to detect. The universe might also have a more complex shape. Some scientists propose it could be a torus, shaped like a giant donut. In this model, space loops back on itself in a different way than a sphere. If the universe were shaped like this, traveling far enough in one direction would still bring you back to where you started, but in a more complicated path. There's no strong evidence for this yet, but scientists continue testing the idea. Another way to think about the universe's shape is by considering its dimensions. We experience space in 3 dimensions: length, width, and height. But if the universe has extra dimensions that we don't directly see, its shape could be far stranger than a simple sphere, saddle, or flat plane. Some theories, like string theory, suggest there may be more than 3 spatial dimensions, which could affect how the universe is shaped. Scientists also look at the way galaxies are arranged in space. If the universe were curved or had a looping structure, there might be repeating patterns in the distribution of galaxies. So far, we don't see any obvious repetition. This supports the idea that the universe is either flat or so vast that any curvature is too large to measure. The shape of the universe also affects its future. If it's flat, it will keep expanding forever. If it's curved like a sphere, it could eventually stop expanding and collapse. If it's curved like a saddle, it will expand faster and faster. Right now, all evidence points to a universe that will continue expanding, driven by dark energy. This suggests that if the universe does have a shape, it is so large that any curvature is beyond what we can measure. Our understanding of the universe's shape has changed over time. Early astronomers thought Earth was the center of the universe. Later, scientists realized Earth orbits the Sun, and the Sun is just one of many stars in the galaxy. Then they learned that our galaxy is just one of billions in the universe. Now, we try to understand how the universe itself is shaped using tools like powerful telescopes, satellites, and deep space observations. Future discoveries could change what we know. New measurements of cosmic background radiation, improved telescope data, or new physics theories could reveal more details about the true structure of space. For now, the best evidence suggests the universe is either completely flat or so large that any curvature is too slight for us to detect. This means space likely stretches on forever, with galaxies moving farther apart as time goes on. The observable universe is the part of the cosmos we can see. Its boundary is set by the farthest light that has had time to reach us since the beginning of the universe. This limit exists because light travels at a finite speed. The universe is about 13.8 billion years old. But because space has expanded, the farthest objects we can detect are now about 46 billion light-years away. Beyond this point, we don't know for certain what exists. Scientists have theories, but no direct evidence. Imagine standing on a beach and looking at the ocean. You can see only as far as the horizon. You know the ocean continues, but you don't know exactly what's beyond that point. The observable universe is like that. The cosmic horizon limits what we can see, but the universe itself may extend far beyond. One of the biggest questions is whether the universe has an edge, or if it goes on forever. If it has an edge, what's beyond it? If it doesn't, does it wrap around in some way? Current models suggest the universe is either infinite or so large that we will never see its full extent. The idea of an infinite universe means space has no boundary. It keeps going, with more galaxies, stars, and planets stretching beyond our view. Another possibility is that the universe is finite but unbounded. This idea is harder to picture. One way to think about it is to imagine walking on Earth's surface. You could keep walking forever and never find an edge. This happens because Earth's surface curves back on itself. If space works the same way on a much larger scale, you could theoretically travel in one direction and eventually return to your starting point, though this would take an unimaginable amount of time. Scientists look for clues about what lies beyond our cosmic horizon by studying the universe we can see. The way galaxies are spread out, the cosmic microwave background radiation, and patterns in the structure of the universe help form hypotheses. If the universe beyond our view is similar to what we observe, it may just be more of the same, more galaxies, stars, and planets arranged in familiar ways. Some theories suggest more exotic possibilities. One idea is that beyond our observable universe, physical laws could be different. The constants of nature, like the strength of gravity or the charge of an electron, might vary in distant regions. If true, this would mean parts of the universe could be very different from what we know. There might be places where stars don't form, where atoms can't exist, or where time behaves in unexpected ways. The multiverse theory adds another layer to this discussion. Some scientists propose that our universe is just one of many. These other universes might exist in a larger multiverse, separate from our own, but governed by different laws of physics. If this is the case, then beyond our observable universe, there could be entirely different realities that we can never access or detect. Another consideration is how the universe changes over time. Space is expanding, and this affects what we can see. Some galaxies are moving away so fast that their light will never reach us. Over billions of years, more of the universe will become unobservable as expansion continues. This means that even though the universe might be infinite, our view of it shrinks over time. In the far future, only a small fraction of today's observable universe will remain visible. Some researchers study cosmic inflation to understand what might be beyond our view. Inflation is the idea that, in the very early universe, space expanded at an incredible rate. This rapid stretching could mean that the observable universe is just a small part of a much larger region shaped by inflation's effects. If this theory is correct, then our universe is just one bubble in a vast cosmic landscape. There's also the question of whether we could ever see beyond our current limits. Technology is improving, and new telescopes allow us to look deeper into space. But no matter how powerful a telescope we build, the speed of light creates a hard boundary. We can never see beyond the region where light has had time to reach us. The only way to gather information about what lies beyond would be indirect, such as detecting gravitational waves or other effects that reach us from unseen regions. The idea of exploring beyond the observable universe raises philosophical questions. If we can never observe these distant regions, do they really exist? Science relies on evidence, and if something is forever beyond our reach, Some argue that it is not a scientific question, but a matter of speculation. Others believe that even without direct observation, logical reasoning and indirect evidence can help us understand what lies beyond. The topic also touches on the nature of infinity. If the universe is infinite, then somewhere beyond our observable patch, there could be another region nearly identical to ours. There could be another version of Earth, another version of you, living a slightly different life. This idea comes from probability. In an infinite universe, every possible arrangement of matter must happen somewhere. But if the universe is finite, then these possibilities might not exist. Observing the cosmic microwave background radiation has provided some hints about the universe's overall shape. So far, the evidence suggests that space is very close to flat, meaning it doesn't curve back on itself noticeably. If this is true, it supports the idea of an infinite universe. But slight deviations could indicate that space does wrap around in some way. One of the strangest possibilities is that our universe could be part of a much larger structure, like a single layer in a higher dimensional space. Some theories suggest that what we see as the universe is just a three-dimensional slice of a more complex reality. If this is true, then beyond our observable universe, there could be entire regions that exist in ways we can't comprehend. Some thinkers speculate about whether it is even meaningful to talk about a beyond if we can never reach it. If the observable universe is all we can ever experience, then for practical purposes, it is the entire universe. But most cosmologists assume that what we see is just a small part of a much larger reality. The question of what lies beyond our observable universe remains one of the biggest mysteries in science. Whether space goes on forever, wraps around itself, or leads to entirely different realms, we may never know for sure. The limits of observation create a boundary that no telescope can cross. Still, by studying what we can see, scientists continue to develop theories about the vast and possibly endless cosmos beyond. The idea that our universe is just one of many is called the Multiverse Hypothesis. This concept suggests that countless other universes exist, each with different physical laws, constants, and histories. Some scientists take this idea seriously, while others see it as speculation. The multiverse challenges our understanding of reality and raises deep questions about space, time, and existence. The idea comes from different areas of physics and cosmology. One version of the multiverse comes from cosmic inflation, a theory about how the universe expanded right after the Big Bang. This theory suggests that space is constantly stretching, and in some regions, this stretching stops, forming bubble-like universes. Our universe would be one of these bubbles, surrounded by many others, each forming under different conditions. If this is true, there could be an infinite number of universes, each with its own version of physics. Another idea comes from quantum mechanics. In quantum theory, particles don't have set locations or states until they are measured. Some interpretations suggest that every possible outcome happens, but in separate, branching universes. This means that every time a choice is made, reality splits into multiple versions. If you flip a coin, there could be one universe where it lands on heads and another where it lands on tails. This is known as the many worlds interpretation. If it's correct, every decision, every random event leads to the creation of new, parallel universes. String theory, another area of physics, also suggests the existence of a multiverse. String theory attempts to unify gravity and quantum mechanics by proposing that the fundamental building blocks of reality are tiny, vibrating strings. This theory predicts extra dimensions beyond the three of space and one of time that we experience. These extra dimensions could allow for different versions of physics, leading to many different possible universes. Some versions of string theory propose a landscape of universes, each with different physical laws and constants. If the multiverse exists, it raises important questions about why our universe is the way it is. Scientists have long wondered why the fundamental constants of nature, such as the strength of gravity or the charge of an electron, have the values they do. If they were slightly different, atoms might not form, stars might not shine, and life as we know it wouldn't exist. This puzzle is known as the fine-tuning problem. If there is only one universe, the fact that everything is so perfectly balanced seems like a huge coincidence. But if there are infinite universes with different physical laws, then it's not surprising that at least one of them has the right conditions for life. This is known as the anthropic principle, the idea that we observe this particular universe because it's the one where we can exist. Even though the multiverse is an interesting idea, it's difficult to test. Science relies on experiments and observations, but if other universes are completely separate from ours, then there may be no way to detect them. Some scientists argue that this makes the multiverse unscientific, since there's no way to prove or disprove it. Others believe that indirect evidence, such as patterns in the cosmic microwave background radiation, the faint glow left over from the Big Bang, might hint at the existence of other universes. Some theories predict that universes can occasionally collide, leaving detectable marks in the sky. So far, no clear evidence of this has been found. Another challenge is that different versions of the multiverse idea come from different areas of physics, and they may not all be talking about the same thing. The multiverse from cosmic inflation is different from the multiverse in quantum mechanics or string theory. Some scientists think that one or more of these ideas will turn out to be correct, while others believe that all of them will eventually be replaced by a deeper understanding of reality. If the multiverse is real, it changes how we think about our place in the cosmos. Instead of being unique, our universe would be just one of many. If the many worlds interpretation of quantum mechanics is correct, then every possible version of history exists somewhere. There could be a universe where Earth never formed, a universe where dinosaurs never went extinct, or a universe where life developed in completely different ways. If there are infinite universes, then there could be versions of you that have made different choices, leading completely different lives. The multiverse also raises philosophical questions. If every possible version of events happens somewhere, does that mean free will is an illusion? Are there copies of us who are identical in every way except for one small detail? If there are infinite universes, does anything truly matter? Or is every possibility inevitable? Some thinkers argue that the multiverse explains everything too easily. If anything that can happen does happen somewhere, then nothing is special. Others argue that even if the multiverse is real, it doesn't change the fact that we live in this universe and must understand it on its own terms. Despite its challenges, the multiverse remains an important topic in physics. Scientists continue to explore its implications through mathematics, computer simulations, and experiments. Some believe that future discoveries in cosmology or quantum mechanics may provide new insights. Others think that the multiverse will remain a philosophical idea rather than a scientific one. Either way, the idea of multiple universes pushes the limits of what we understand about reality. Quantum mechanics and the cosmos seem like two separate realms. One deals with the very small particles, atoms, and fundamental forces. The other covers the very large, galaxies, black holes, and the universe itself. But scientists have long suspected that the two are connected. The problem is that the laws governing them don't seem to fit together. Classical physics, which explains the motion of planets and stars, breaks down when applied to quantum scales. Meanwhile, quantum physics, which governs particles, doesn't scale up smoothly to explain gravity. Understanding this connection could change our entire view of reality. Quantum mechanics suggests that at the smallest level, the universe behaves unpredictably. A particle can be in two places at once. It can pass through barriers as if they aren't there. It can influence another particle instantly, no matter how far apart they are. None of these behaviors align with classical physics, which relies on predictable cause and effect. Yet, quantum mechanics is the most successful scientific theory ever tested. Its predictions have been confirmed time and time again. One of the most puzzling aspects of quantum physics is superposition. A particle doesn't exist in just one place, but in all possible places at once, until it is measured. The famous Schrödinger's cat thought experiment illustrates this. A cat in a box, along with a radioactive atom and a vial of poison, exists in a state where it is both alive and dead at the same time. Only when someone opens the box does reality choose one state or the other. This is not just an oddity of laboratory experiments. The entire universe might operate this way at the most fundamental level. Then there's quantum entanglement. When two particles become entangled, they stay connected no matter how far apart they are. Changing one particle instantly affects the other, even if they are on opposite sides of the universe. Einstein called this spooky action at a distance because it seemed to violate the laws of relativity. But experiments show that entanglement is real. The universe itself might be woven together by these invisible, instantaneous connections. This raises an important question. Does quantum mechanics play a role in the structure of the universe? Physicists suspect that at the moment of the Big Bang, the universe was governed by quantum effects. Space itself was uncertain, fluctuating between different possible states before settling into what we see today. Some scientists propose that the entire universe exists in a kind of quantum superposition. This idea could help explain why the universe appears fine-tuned for life. In an infinite number of quantum possibilities, we exist in the one that allows life to thrive. Black holes also provide clues to the quantum nature of the cosmos. A black hole is a region where gravity is so strong that nothing can escape, not even light. Classical physics says that anything falling into a black hole is lost forever, but quantum mechanics suggests otherwise. Theoretical physicist Stephen Hawking showed that black holes slowly evaporate by emitting radiation, now called Hawking radiation. This creates a paradox. If information falls into a black hole and the black hole evaporates, what happens to that information? Quantum mechanics says information cannot be destroyed, but general relativity suggests it can. This contradiction remains one of the biggest mysteries in physics. Some scientists believe that space and time themselves emerge from quantum effects. Instead of viewing space as a static backdrop, they suggest it is made up of tiny quantum bits of information. In this view, space-time is not continuous, but pixelated, like a digital image. The holographic principle builds on this idea. It suggests that everything we experience in 3 dimensions may actually be encoded on a 2-dimensional surface. This is based on studies of black holes, where all the information inside them can be described by data on their surface. If this applies to the universe as a whole, then reality as we know it might be a projection of quantum information. Quantum mechanics also affects how we think about time. In classical physics, time moves in one direction, from past to future. But in quantum mechanics, time appears to have no preferred direction. Some equations suggest that time could flow backward just as easily as forward. This idea raises strange possibilities. Could the future influence the past? Could events be predetermined by quantum states that haven't even happened yet? These questions remain unanswered, but they challenge our basic understanding of time itself. The link between quantum mechanics and gravity is another open question. Gravity, as described by Einstein's general relativity, is a smooth and continuous force. Quantum mechanics, on the other hand, describes nature in discrete units. This mismatch makes it impossible to unify the two theories. One possible solution is quantum gravity, a still developing theory that attempts to describe gravity using quantum principles. String theory and loop quantum gravity are 2 leading candidates, but neither has been confirmed. If quantum gravity is ever discovered, it could rewrite our understanding of the cosmos. Even the vacuum of space is not truly empty. Quantum mechanics predicts that space is filled with tiny, short-lived particles that pop in and out of existence. These virtual particles create a subtle energy known as vacuum energy. Some physicists think this energy could be responsible for dark energy, the mysterious force causing the universe to expand faster and faster. If quantum fluctuations can shape the structure of space itself, they may hold the key to understanding the fate of the universe. At the deepest level, quantum mechanics suggests that reality is not solid and fixed, but built on probabilities. The universe, at its core, may be a collection of possibilities rather than definite outcomes. Some interpretations go even further. The many worlds interpretation proposes that every quantum event splits the universe into multiple realities. Every possible outcome happens, but in separate, parallel universes. If true, then infinite versions of reality exist, each following a slightly different path. The biggest challenge in understanding the link between quantum mechanics and the cosmos is testing these ideas. Quantum effects are easy to observe in labs, but hard to detect on cosmic scales. Experiments with quantum entanglement have been carried out using satellites, but proving that space itself behaves quantum mechanically is another challenge entirely. Some scientists are looking at cosmic microwave background radiation, the afterglow of the Big Bang, for quantum fingerprints. Others are studying gravitational waves, ripples in spacetime, to see if they reveal signs of quantum behavior. No matter where this research leads, one thing is clear: quantum mechanics and the cosmos are deeply connected. The universe, from its birth to its far future, may be ruled by the same strange and counterintuitive laws that govern subatomic particles. The more we learn, the more reality seems to defy common sense. The universe might not just be a vast expanse of stars and galaxies, but a quantum system woven together by probabilities, entanglements, and unseen forces. Quantum mechanics and the cosmos seem like two separate realms. One deals with the very small particles, atoms, and fundamental forces. The other covers the very large, galaxies, black holes, and the universe itself. But scientists have long suspected that the two are connected. The problem is that the laws governing them don't seem to fit together. Classical physics, which explains the motion of planets and stars, breaks down when applied to quantum scales. Meanwhile, quantum physics, which governs particles, doesn't scale up smoothly to explain gravity. Understanding this connection could change our entire view of reality. Quantum mechanics suggests that at the smallest level, the universe behaves unpredictably. A particle can be in two places at once. It can pass through barriers as if they aren't there. It can influence another particle instantly, no matter how far apart they are. None of these behaviors align with classical physics, which relies on predictable cause and effect. Yet, quantum mechanics is the most successful scientific theory ever tested. Its predictions have been confirmed time and time again. One of the most puzzling aspects of quantum physics is superposition. A particle doesn't exist in just one place, but in all possible places at once, until it is measured. The famous Schrödinger's cat thought experiment illustrates this. A cat in a box, along with a radioactive atom and a vial of poison, exists in a state where it is both alive and dead at the same time. Only when someone opens the box does reality choose one state or the other. This is not just an oddity of laboratory experiments. The entire universe might operate this way at the most fundamental level. Then there's quantum entanglement. When two particles become entangled, they stay connected no matter how far apart they are. Changing one particle instantly affects the other, even if they are on opposite sides of the universe. Einstein called this spooky action at a distance because it seemed to violate the laws of relativity. But experiments show that entanglement is real. The universe itself might be woven together by these invisible, instantaneous connections. This raises an important question. Does quantum mechanics play a role in the structure of the universe? Physicists suspect that at the moment of the Big Bang, the universe was governed by quantum effects. Space itself was uncertain, fluctuating between different possible states before settling into what we see today. Some scientists propose that the entire universe exists in a kind of quantum superposition. This idea could help explain why the universe appears fine-tuned for life. In an infinite number of quantum possibilities, we exist in the one that allows life to thrive. Black holes also provide clues to the quantum nature of the cosmos. A black hole is a region where gravity is so strong that nothing can escape, not even light. Classical physics says that anything falling into a black hole is lost forever, but quantum mechanics suggests otherwise. Theoretical physicist Stephen Hawking showed that black holes slowly evaporate by emitting radiation, now called Hawking radiation. This creates a paradox. If information falls into a black hole and the black hole evaporates, what happens to that information? Quantum mechanics says information cannot be destroyed, but general relativity suggests it can. This contradiction remains one of the biggest mysteries in physics. Some scientists believe that space and time themselves emerge from quantum effects. Instead of viewing space as a static backdrop, they suggest it is made up of tiny quantum bits of information. In this view, space-time is not continuous, but pixelated, like a digital image. The holographic principle builds on this idea. It suggests that everything we experience in 3 dimensions may actually be encoded on a 2-dimensional surface. This is based on studies of black holes where all the information inside them can be described by data on their surface. If this applies to the universe as a whole, then reality as we know it might be a projection of quantum information. Quantum mechanics also affects how we think about time. In classical physics, time moves in one direction, from past to future. But in quantum mechanics, time appears to have no preferred direction. Some equations suggest that time could flow backward just as easily as forward. This idea raises strange possibilities. Could the future influence the past? Could events be predetermined by quantum states that haven't even happened yet? These questions remain unanswered, but they challenge our basic understanding of time itself. The link between quantum mechanics and gravity is another open question. Gravity, as described by Einstein's general relativity, is a smooth and continuous force. Quantum mechanics, on the other hand, describes nature in discrete units. This mismatch makes it impossible to unify the two theories. One possible solution is quantum gravity, a still developing theory that attempts to describe gravity using quantum principles. String theory and loop quantum gravity are two leading candidates, but neither has been confirmed. If quantum gravity is ever discovered, it could rewrite our understanding of the cosmos. Even the vacuum of space is not truly empty. Quantum mechanics predicts that space is filled with tiny, short-lived particles that pop in and out of existence. These virtual particles create a subtle energy known as vacuum energy. Some physicists think this energy could be responsible for dark energy, the mysterious force causing the universe to expand faster and faster. If quantum fluctuations can shape the structure of space itself, they may hold the key to understanding the fate of the universe. At the deepest level, quantum mechanics suggests that reality is not solid and fixed, but built on probabilities. The universe, at its core, may be a collection of possibilities rather than definite outcomes. Some interpretations go even further. The many worlds interpretation proposes that every quantum event splits the universe into multiple realities. Every possible outcome happens, but in separate, parallel universes. If true, then infinite versions of reality exist, each following a slightly different path. The biggest challenge in understanding the link between quantum mechanics and the cosmos is testing these ideas. Quantum effects are easy to observe in labs, but hard to detect on cosmic scales. Experiments with quantum entanglement have been carried out using satellites, but proving that space itself behaves quantum mechanically is another challenge entirely. Some scientists are looking at cosmic microwave background radiation, the afterglow of the Big Bang, for quantum fingerprints. Others are studying gravitational waves, ripples in spacetime, to see if they reveal signs of quantum behavior. No matter where this research leads, one thing is clear. Quantum mechanics and the cosmos are deeply connected. The universe, from its birth to its far future, may be ruled by the same strange and counterintuitive laws that govern subatomic particles. The more we learn, the more reality seems to defy common sense. The universe might not just be a vast expanse of stars and galaxies, but a quantum system woven together by probabilities, entanglements, and unseen forces. Some scientists and philosophers ask if the universe could be conscious. This idea might sound strange, but it comes from real questions about how consciousness works and how the universe is structured. Consciousness is the ability to have experiences, to be aware. People experience it every day. You know what it feels like to be hungry, to hear music, to remember something. But no one fully understands why these experiences happen or where they come from. The brain is involved, but no one can explain exactly how brain activity turns into thoughts and feelings. Some researchers wonder if consciousness is not just in the brain, but instead a fundamental part of reality. This is called panpsychism. It suggests that everything in the universe, even tiny particles, has some level of awareness. If this is true, then the universe itself might have some kind of mind. Scientists usually explain the universe using physical laws. Planets orbit stars because of gravity. Galaxies form as gas and dust collapse under their own weight. Everything follows predictable rules. But if the universe is conscious, that would mean it is more than just a collection of objects following laws. It would mean the universe has experiences in some way. One argument for this idea comes from how brains work. A brain is made of billions of cells called neurons. Each neuron is not conscious by itself. But when many neurons connect, consciousness appears. Some scientists ask if the universe works the same way. Galaxies, stars, and planets all connect through gravity and other forces. Maybe, when enough things are linked together, a form of awareness emerges. If a brain can create a mind from simple parts, maybe the universe does something similar. Others look at quantum physics for clues. At a small scale, particles behave in strange ways. They can exist in two places at once, or change depending on whether they are observed. Some scientists think this means consciousness plays a role in shaping reality. If observation affects how particles behave, that suggests a connection between thought and the physical world. Some take this idea further and say that consciousness might not come from matter at all. Instead, matter might come from consciousness. There is also the idea that the universe processes information like a giant brain. Scientists studying networks see similarities between the way galaxies connect and the way neurons connect. If the universe organizes itself like a brain, could it also think? This is a difficult question because no one fully understands how thoughts work. Even inside a human brain, scientists don't know exactly how electrical signals turn into ideas and feelings. If the universe does think, it might do so in a way that is completely different from human thought. Some scientists argue against this idea. They say consciousness needs a complex system like a brain to exist. The universe is big, but that doesn't mean it has a mind. Just because galaxies and neurons look similar doesn't mean they work the same way. A tornado and a blender both spin, but that doesn't mean a tornado is a kitchen appliance. Another issue is that people tend to see patterns where there are none. The human brain is good at finding meaning in randomness. Sometimes it sees faces in clouds or hears voices in the wind. The idea that the universe is conscious could be another example of this. People see something big and complex and assume it must have a mind. There's also the question of what it would mean if the universe were conscious. Would it have thoughts and emotions? Would it have goals? If the universe has a mind, does that mean it also has a purpose? These are difficult questions. Human minds are shaped by experiences. The universe, if it has a mind, would be nothing like a person. It might not think in a way that humans can understand. Some religious and spiritual traditions say the universe has a kind of awareness. Many ancient beliefs describe the world as alive. Some people believe the universe is a single, connected being. Modern science does not prove this, but it does not completely rule it out either. This idea also connects to artificial intelligence. If computers become advanced enough, will they be conscious? Right now, AI can process information, but does not have thoughts or feelings. But if a complex enough system can create consciousness, then maybe the universe, as the most complex system of all, has already done so. The search for consciousness in the universe is tied to the search for the origins of thought. Scientists do not fully understand where consciousness comes from, and until they do, the question of whether the universe is conscious will remain open. A black hole is a region in space where gravity is so strong that nothing can escape, not even light. The event horizon is the boundary around a black hole. Once something crosses this boundary, it cannot come back. People often imagine the event horizon as a kind of surface, but it's not a physical structure. It's just a point where gravity becomes too strong for anything to resist. To understand the event horizon, imagine throwing a ball into the air. On Earth, the ball goes up, slows down, and falls back. If you throw it harder, it goes higher before coming back. If you could throw it fast enough, about 11 kilometers per second, it would never return. This is called escape velocity. On a black hole, the escape velocity at the event horizon equals the speed of light. Nothing can travel faster than light, so nothing can escape once it gets too close. A person falling toward a black hole would experience strange effects. Far from the black hole, everything would seem normal. As they got closer, gravity would start to stretch them. This happens because gravity is stronger closer to the black hole and weaker farther away. Scientists call this effect spaghettification. If the black hole were small, the stretching would tear the person apart before they reached the event horizon. If the black hole were large, they might cross the event horizon without noticing anything unusual at first. From an outside observer's point of view, the person would seem to slow down as they approached the event horizon. This happens because gravity affects time. The closer something gets to a black hole, the slower time moves for it compared to someone farther away. To the outside observer, the person would never actually appear to cross the event horizon. Instead, they would seem to freeze in place, gradually fading as the light from them gets redder and dimmer. This effect is called gravitational time dilation. Inside the event horizon, the rules of physics change. Space and time switch roles in a sense. Normally, time moves forward, and people can move freely in space. Inside the event horizon, moving forward in time means moving toward the center of the black hole. There is no way to stop or turn around. It's like being in a river that flows faster than you can swim. No matter how hard you try, you can't fight the current. The center of the black hole is called the singularity. Here, gravity becomes infinitely strong, and the normal laws of physics break down. Scientists do not fully understand what happens at the singularity. Einstein's general theory of relativity predicts that everything falling into the black hole is crushed into an infinitely small point, but quantum mechanics suggests something else might happen. Because the two theories do not agree, physicists are searching for a deeper understanding of gravity. One of the most famous discoveries about black holes is that they are not completely black. In the 1970s, Stephen Hawking showed that black holes can emit radiation. This is called Hawking radiation. It happens because of quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually evaporate. For small black holes, this could happen quickly. For large black holes, it could take longer than the age of the universe. The idea of an event horizon creates deep questions about physics and information. In everyday life, when something falls into a fire, the matter turns to ash, but the information about it is not lost. Scientists believe that information should never be destroyed, even in extreme conditions. If something falls into a black hole, does its information disappear forever? This is known as the black hole information paradox. Some physicists believe that information might escape through Hawking radiation, but no one knows for sure. The study of black holes has led to new ideas about the universe. Some theories suggest that black holes might connect to other regions of space or even other universes. These ideas involve wormholes, which are hypothetical tunnels in space-time. No evidence for wormholes exists, but they're allowed by Einstein's equations. If real, they could provide shortcuts through space, though they would likely collapse too quickly for travel. Scientists have found strong evidence for black holes by studying their effects on nearby objects. The best example is the supermassive black hole at the center of our galaxy, called Sagittarius A. Astronomers have tracked stars orbiting an invisible object there. The way these stars move shows that the object must be a black hole with a mass millions of times greater than the Sun. In 2019, the Event Horizon Telescope captured an image of the black hole at the center of another galaxy, M87. This was the first direct visual proof of an event horizon. Black holes exist in different sizes. Stellar black holes form when large stars run out of fuel and collapse. These can be a few times the mass of the Sun. Supermassive black holes, found in galaxy centers, can be millions or billions of times the Sun's mass. Some theories suggest that tiny black holes could have formed in the early universe. If they exist, they would be too small to see, but might still leave detectable effects. Understanding the event horizon is important for physics. It challenges ideas about space, time, and gravity. It also raises questions about what happens to matter and information in extreme conditions. Scientists continue to study black holes, hoping to uncover deeper truths about the universe. The universe was once a dark, empty place. After the Big Bang, it took hundreds of millions of years for the first stars and galaxies to form. In the beginning, space was filled with hot, dense gas. Hydrogen and helium, the simplest elements, floated freely. There were no stars, no planets, and no galaxies. Light did not yet exist in the way we know it today. The universe was in a period called the Cosmic Dark Ages. Over time, tiny fluctuations in the gas began to form. Gravity pulled the gas together, creating dense clumps. These clumps grew larger as they attracted more gas. As the gas gathered, the pressure and temperature inside increased. When the temperature became hot enough, nuclear fusion began. This was the birth of the first stars. These early stars were different from the stars we see today. They were much larger, hotter, and shorter lived. Some of them were hundreds of times more massive than the Sun. Because they formed from pure hydrogen and helium, they burned hotter and produced intense ultraviolet radiation. This radiation started breaking apart hydrogen atoms in space, a process called reionization. This event changed the universe forever by allowing light to travel freely. As these stars burned, they fused hydrogen into helium, then into heavier elements like carbon and oxygen. But their lives were short. In just a few million years, many of them exploded as supernovae. These explosions released heavy elements into space, seeding the next generation of stars. Over time, new stars formed with these heavier elements, leading to the creation of planets and, eventually, life. The first galaxies formed when groups of these stars clustered together. Gravity pulled stars and gas into rotating structures. The earliest galaxies were small and irregularly shaped. Over billions of years, they merged with each other, growing larger. Some of these early mergers formed the foundations of the massive galaxies we see today, including the Milky Way. Black holes also played a key role. Some of the first stars collapsed into black holes after they died. Over time, these black holes grew as they pulled in gas and merged with others. Some became supermassive black holes, sitting at the centers of galaxies. These black holes influenced galaxy formation by shaping how gas moved and how new stars formed. The universe looked very different in its early days. The sky would have been filled with bright, massive stars, unlike anything we see today. Galaxies were smaller and more chaotic, constantly colliding and merging. Over time, order began to emerge. The Milky Way, for example, formed from smaller galaxies combining over billions of years. Its spiral structure took shape as gravity organized the stars and gas into a disk. The study of the first stars and galaxies comes from telescopes that look deep into space. Since light takes time to travel, looking at distant galaxies is like looking back in time. The Hubble Space Telescope and the James Webb Space Telescope have captured images of some of the earliest galaxies, showing them as they were billions of years ago. Astronomers also use radio waves and infrared light to study the faint glow left by the first stars. Some of this light has been stretched by the expansion of the universe, shifting it into wavelengths that human eyes cannot see. By studying this ancient light, scientists can piece together the story of how the cosmos evolved. The first stars and galaxies set the stage for everything that followed. Without them, there would be no heavier elements, no planets, and no life. The way these early structures formed determined how galaxies look today. The Milky Way, for example, has its shape and structure because of the early mergers and star formations that took place billions of years ago. Even though scientists have learned a lot, many questions remain. How did the first black holes grow so quickly? Why did some galaxies stop forming stars while others continued? What caused the first supermassive black holes to appear? Researchers continue to search for answers using more advanced telescopes and computer models. By studying the birth of the first stars and galaxies, we learn more about our own origins. The elements in our bodies were forged in those first explosions. The structure of our galaxy traces back to those early mergers. Everything we see today started in that distant, ancient past, when the first light pierced the darkness and the universe took its first steps toward what it is now. Wormholes are theoretical shortcuts through space-time. Imagine two distant points in space. Instead of traveling the long way around, a wormhole could connect them directly, making the trip almost instant. This idea comes from Einstein's theory of general relativity, which suggests space-time can bend and fold. If this is true, a wormhole could act like a tunnel between different regions of the universe. The concept of wormholes is not new. In 1935, Albert Einstein and Nathan Rosen proposed them as Einstein-Rosen bridges. Their equations showed how black holes might connect different points in space. But these bridges collapsed too quickly for anything to pass through. Later, physicists like Kip Thorne explored whether a stable wormhole could exist. A wormhole has two openings and a tunnel-like passage between them. If stable, a spaceship could enter one side and exit the other, no matter how far apart the openings are. The problem is keeping the tunnel open. gravity should make it collapse instantly. To prevent that, something needs to push outward against the inward pull of gravity. This is where exotic matter comes in. Exotic matter is not ordinary matter like stars and planets. It has unusual properties, including negative energy density. Negative energy could act like an anti-gravity force, keeping the wormhole open. Scientists have observed small amounts of negative energy in quantum experiments, but not enough to stabilize a wormhole. The idea of using wormholes for space travel is tempting. A trip to the nearest star, Proxima Centauri, takes over 4 years at light speed. With a wormhole, the journey could be instantaneous. If wormholes could connect different galaxies, intergalactic travel would become possible. Some theories suggest wormholes could link different times as well as places. This means traveling through a wormhole could be a form of time travel. If one end of a wormhole moves at near light speed while the other stays still, time passes differently for each end. Someone entering one side might exit in the past or future. This creates paradoxes, like the possibility of meeting your past self. So far, no one has found a natural wormhole. Black holes might be related, but their gravity is too strong for safe passage. If a wormhole exists in space, it would be hard to detect. It might bend light around it in strange ways, similar to how a glass lens bends light. Scientists look for these effects in the sky, but have not found any definite signs. Some theories suggest small wormholes could exist on a quantum scale. These would be microscopic, appearing and disappearing in tiny fractions of a second. If a way existed to stabilize and enlarge them, they might become useful for travel. This idea is purely theoretical. Building a wormhole would require negative energy in large amounts. No known process can produce enough of it. Even if it were possible, controlling the shape and size of a wormhole would be another challenge. It would need to be large enough for a spacecraft, but not collapse under its own gravity. Even if stable wormholes existed, they might not be safe. Space near the entrance could be filled with intense radiation. Any matter passing through might stretch or tear apart due to extreme forces. If a wormhole connected different parts of the universe, high-energy particles could rush through, making travel dangerous. Science fiction often features wormholes as a way to explore the galaxy. Movies and books portray them as portals that instantly connect distant locations. While these stories take creative liberties, they reflect real physics ideas. Shows like Star Trek and movies like Interstellar explore how wormholes might work. Practical space travel depends on finding new ways to move through space quickly. Current rocket technology is too slow for interstellar travel. If wormholes could be controlled, they would provide the fastest route between distant worlds. But without evidence of their existence, they remain a theoretical concept. Research continues in different areas of physics to explore if wormholes could ever be possible. Quantum physics and relativity might hold clues. If scientists discover how to create or stabilize them, they could change the way we think about space travel. For now, wormholes remain an idea in equations and science fiction. They show how space-time could work in ways we don't yet understand. If one day they become real, they could redefine the limits of human exploration. Physicists believe that our universe may have more dimensions than the 3 of space and 1 of time that we experience. This idea comes from attempts to explain gravity, quantum mechanics, and the structure of the cosmos. Most of us think of the world in terms of length, width, and height. These are the 3 spatial dimensions that define how we move and interact with objects. Time acts as the 4th dimension, always moving forward and shaping our experience of reality. But theories in physics suggest that more dimensions may exist, hidden from our senses, but influencing the universe in ways we have yet to fully understand. One of the earliest ideas of extra dimensions came from attempts to unify gravity with the other forces of nature. Gravity is strange compared to the other fundamental forces: electromagnetism, the strong nuclear force, and the weak nuclear force. These 3 forces fit well within quantum mechanics, the theory that explains the behavior of particles at very small scales. Gravity does not. Instead, gravity follows the rules of general relativity, a theory that describes how space and time bend in response to mass and energy. The fact that gravity does not fit with quantum mechanics has led scientists to search for a deeper theory that brings them together. One such attempt is string theory, which suggests that everything in the universe is made of tiny vibrating strings instead of point-like particles. According to string theory, these strings can only vibrate in a way that makes sense if the universe has at least 10 dimensions, 9 of space and 1 of time. If these extra dimensions exist, why don't we see them? Scientists think they could be curled up or compactified at such small scales that they remain hidden from our senses. Picture a garden hose stretching across a field. From far away, it looks like a one-dimensional line. But up close, you see that the hose has thickness. If you were a tiny ant walking on the surface of the hose, you would experience an extra dimension curled around the hose. Some physicists believe that extra dimensions in our universe work the same way. Another approach comes from a theory called brain cosmology. In this view, our universe exists as a three-dimensional brain floating inside a higher dimensional space. A brain is short for membrane, meaning a surface or structure within a larger space. If this idea is correct, then extra dimensions might not be small at all. Instead, they could be vast, but we remain confined to our three-dimensional brain, unable to detect them. Think of a sheet of paper floating inside a room. If tiny creatures lived only on the surface of the paper, they might never know that an entire three-dimensional space surrounds them. We could be in the same situation, trapped on a three-dimensional brain without direct access to the higher dimensional space around us. Some versions of these theories suggest that gravity might be able to move through extra dimensions, even if other forces cannot. Gravity is much weaker than the other fundamental forces. A small refrigerator magnet can lift a paperclip against the entire gravitational pull of the Earth. Some physicists think this weakness might be explained if gravity leaks into extra dimensions. If we could test gravity at very small distances, we might find evidence of these hidden dimensions. So far, experiments have not revealed any deviations from what we expect in three-dimensional space, but the search continues. There are also more abstract ways to think about extra dimensions. In some mathematical descriptions of physics, dimensions do not have to be physical in the way we imagine. They can represent different properties of particles, forces, or quantum states. Some physicists explore whether time itself might have more than one dimension, though no experiment has confirmed this idea. If extra dimensions exist, what could they mean for the universe and our understanding of reality? If we found a way to access them, could we travel through them to reach distant parts of space? Some theories suggest that higher dimensions might allow for shortcuts through space-time, similar to wormholes. A wormhole is a hypothetical tunnel that connects two distant points in space. If higher dimensions exist, they might provide a framework for such shortcuts, though we do not yet know if they are physically possible. Another question is whether life could exist in higher dimensions. If a being could move freely in a fourth spatial dimension, it would see the inside of a closed three-dimensional object without opening it. Imagine a two-dimensional being living on a flat surface. If you were a three-dimensional observer, you could lift that being off its surface, place it somewhere else, or even see inside structures that would be closed in 2 dimensions. If higher dimensional beings existed, they might see our entire universe in ways we cannot comprehend. Higher dimensions could also change the way we think about fundamental physics. If reality has more dimensions than we experience, our understanding of particles, forces, and even time itself may be incomplete. Some physicists believe that hidden dimensions might explain why certain physical constants, such as the strength of gravity or the charge of an electron, have the values they do. If these constants are influenced by higher dimensional geometry, then understanding extra dimensions might help us solve some of the biggest mysteries in physics. Scientists have proposed several ways to test for extra dimensions. One approach involves searching for deviations in gravity's behavior at very short distances. If extra dimensions exist, gravity might behave differently than expected when measured on tiny scales. Another method involves studying high-energy particle collisions. The Large Hadron Collider, the world's most powerful particle accelerator, smashes particles together at nearly the speed of light. Some theories predict that if extra dimensions exist, these collisions might produce tiny black holes or other unusual effects that could reveal their presence. So far, experiments have not found direct evidence of extra dimensions. That does not mean they do not exist. It could mean that they are harder to detect than we currently understand. If they are real, they could reshape our view of the universe in profound ways. The idea that reality might extend beyond what we perceive is both fascinating and humbling. Whether or not extra dimensions exist, the search for them continues to push the boundaries of our knowledge and our imagination. Humanity may one day leave Earth and settle among the stars. Right now, space travel is slow and expensive. No human has traveled beyond the moon, and even sending robots to nearby planets takes years. But the challenges of interstellar travel go far beyond distance. Space is harsh. It has no air, extreme temperatures, and deadly radiation. Any journey to another star system would require solving problems that we have never faced before. The closest star to Earth is Proxima Centauri, about 4.2 light-years away. That means light, which moves at nearly 300,000 kilometers per second, takes over 4 years to get there. The fastest spacecraft ever built, Voyager 1, moves at about 17 kilometers per second. At that speed, it would take over 70,000 years to reach Proxima Centauri. Clearly, we need a better way to travel if we ever hope to reach another star within a human lifetime. One possibility is nuclear propulsion. A nuclear-powered spaceship could be much faster than anything we have now. Some designs use small nuclear explosions to push a spacecraft forward, while others rely on nuclear reactors to heat and expel fuel at high speeds. Scientists have considered nuclear propulsion for decades, but no one has built a working system for interstellar travel. A more advanced idea is antimatter propulsion. When antimatter and matter collide, they release huge amounts of energy. If we could harness that energy, we could build a spacecraft moving at a large fraction of the speed of light. The problem is that antimatter is rare and difficult to produce. Right now, making even a few grams costs billions of dollars. Another idea is the light sail. Instead of carrying heavy fuel, a spacecraft with a light sail could use energy from powerful lasers on Earth to push it forward. Since light has no mass but still carries momentum, a strong enough laser could accelerate a light sail to high speeds. The Breakthrough Starshot project proposes sending tiny probes to Proxima Centauri using this method. These probes would be no bigger than a computer chip and could reach 20% of the speed of light. At that speed, they could reach Proxima Centauri in about 20 years. But keeping them intact and communicating with them from such a distance would be another challenge. Even if we solve the problem of getting to another star, we still need a way to survive once we get there. Space is mostly empty, but it is not safe. Cosmic radiation, solar flares, and micrometeoroids could damage a spaceship or harm the people inside. Any long-term space journey would need strong shielding, reliable life support, and a way to generate food and water. One way to solve this is by creating self-sustaining habitats. Instead of bringing everything from Earth, we could recycle air, water, and food. Plants could turn carbon dioxide into oxygen while providing food. Special bacteria could process waste into useful materials. Scientists have tested small-scale versions of these systems on Earth and the International Space Station, but making a completely closed system that works for decades is still an unsolved problem. A more extreme idea is putting travelers into suspended animation. Instead of staying awake for decades, they could be put into a deep sleep, slowing down their metabolism to use less food and oxygen. Some animals on Earth, like bears and frogs, can hibernate for months, and researchers are studying ways to do something similar for humans. Medical teams have already used cold temperatures to slow down patients' metabolism in emergency situations. If we perfect this technique, it could make long space journeys easier. If we find a way to reach another star, we need to decide where to go. Scientists have discovered thousands of exoplanets, but only a few might be habitable. The best candidates are planets in the habitable zone of their stars, where temperatures allow liquid water to exist. Proxima b, a planet orbiting Proxima Centauri, is one such world. But just because a planet is in the right zone does not mean it is actually habitable. It could have no atmosphere or be covered in toxic gases. Some scientists suggest sending robotic scouts ahead of humans to check conditions. If we find a good planet, the next challenge is settling there. Humans are used to Earth's gravity, atmosphere, and environment. Any new world would be different. If the gravity is too strong, movement might be difficult. If it is too weak, bones and muscles could weaken over time. An atmosphere with the wrong mix of gases could make breathing impossible. Even if a planet has water and air, we would need to test them to make sure they are safe. One option is terraforming, changing a planet's environment to make it more like Earth. This could mean releasing gases to create a thicker atmosphere, melting ice to create lakes and rivers, or planting special microbes to change the air's composition. Mars is often suggested as a candidate for terraforming. It has ice, carbon dioxide, and a day length similar to Earth's. But turning Mars into a second Earth would take centuries, and the technology to do it does not yet exist. Instead of changing planets, we could adapt ourselves. Genetic engineering or cybernetic enhancements might allow humans to survive in places that would normally be deadly. Future settlers might have lungs modified to breathe different air, skin resistant to radiation, or even artificial bodies that do not need food and water. If interstellar travel becomes possible, it could change everything. Right now, all humans live on Earth, but if we spread to other star systems, we would no longer be tied to one planet. Over thousands of years, different groups could evolve separately, creating new cultures, languages, and even new species. Some civilizations might prefer to stay in space, living on giant stations instead of planets. Others might seek out Earth-like worlds and try to recreate what they left behind. The journey to the stars will not happen overnight. It took thousands of years for humans to spread across Earth, and space is far more difficult to travel. But history shows that when people face challenges, they find solutions. If interstellar travel becomes possible, it will not be because of one great invention, but because of many small steps, each solving a different problem. Right now, the biggest barriers are speed, survival, and self-sufficiency. Solving any one of these problems would be a major breakthrough. If we find a way to travel faster, we could reach other stars without needing suspended animation. If we develop better ways to survive in space, we could stay in space longer. If we create self-sustaining habitats, we could build settlements anywhere. Space agencies and private companies are already working on some of these technologies. NASA is testing nuclear propulsion. SpaceX is developing reusable rockets that could make space travel cheaper. Scientists are studying ways to grow food in space and recycle air and water. These projects are small steps toward a much bigger goal. If humanity ever reaches another star, it will be one of the greatest achievements in history. But for now, it remains a challenge waiting to be solved. Time is one of the most familiar concepts in everyday life. People experience it when they wake up in the morning, count the minutes before an important event, or reflect on the past. Yet, despite its presence, no one fully understands what time is. Scientists and philosophers have debated its nature for centuries. Is it something real that flows forward like a river? Or is it just a way humans make sense of change? These questions remain open, but physics has revealed some strange properties of time that challenge common sense. In everyday life, time seems simple. It moves forward from past to future. A child grows into an adult. A tree sprouts from a seed, reaches full size, and eventually decays. People remember yesterday, but they can't remember tomorrow. This makes it seem like time has a direction. It flows like a one-way street. In physics, this idea is called the arrow of time. But the laws of physics don't actually require time to move in one direction. Most equations work just as well if time runs backward. If someone watches a video of a ball rolling down a hill, it's clear which way time is moving. But if the same video is played in reverse, the ball rolling uphill doesn't break any fundamental laws of physics. The equations allow it. So why doesn't it happen in real life? The answer seems to come from entropy. Entropy is a measure of disorder. Left alone, things tend to become more disorganized over time. A dropped egg breaks, but a broken egg never comes back together. A cup of coffee cools down, but a cold cup of coffee doesn't suddenly heat up. These changes all increase entropy. This tendency for things to move from order to disorder is part of the second law of thermodynamics. This law gives time its apparent direction. When entropy increases, time moves forward. If entropy could somehow decrease, time might seem to run in reverse. In small, isolated cases, this does happen. On a tiny scale, in the world of atoms and molecules, particles sometimes move in ways that look like they're going backward in time. But on a larger scale, the universe as a whole moves toward disorder, keeping time flowing in one direction. Time also behaves differently depending on motion and gravity. In daily life, a second feels like the same length everywhere. But Albert Einstein's theory of relativity showed that time is not fixed. It stretches and shrinks depending on how fast something moves or how strong a gravitational field is. This effect is called time dilation. An astronaut on a fast-moving spaceship would age more slowly than someone on Earth. If they traveled near the speed of light, a journey that felt like a few years to them might last centuries on Earth. This is not just theory. Scientists have tested time dilation using extremely precise atomic clocks. When one clock stays on the ground and another is flown in a high-speed jet, they tick at slightly different rates. GPS satellites also experience this effect. Their clocks run faster than those on Earth because they feel less gravity. Engineers must adjust for this difference so that GPS signals remain accurate. Gravity also affects time in another way. The stronger the gravity, the slower time moves. This was first confirmed in an experiment where two atomic clocks were placed at different heights. The clock closer to the ground, where gravity is slightly stronger, ticked more slowly than the higher clock. This effect, called gravitational time dilation, becomes extreme near black holes. A person orbiting close to a black hole would experience time much more slowly than someone farther away. If they stayed too long and then returned to Earth, they might find that years or centuries had passed while they only felt minutes or hours. Despite these discoveries, the nature of time is still not fully understood. Some physicists believe time is just an illusion. According to this view, time is not a fundamental part of the universe, but instead a way humans organize events. They argue that all moments in time exist at once, like frames of a film. In this block universe idea, past, present, and future all exist simultaneously, and time only feels like it moves because of how people experience it. This idea is hard to accept because it goes against human intuition. People feel like the past is gone, the present is real, and the future has not happened yet. But in the equations of physics, there is no clear distinction between past and future. Another mystery is whether time had a beginning. The Big Bang Theory suggests the universe started from a hot, dense state nearly 14 billion years ago. If time is tied to the universe, then time itself may have begun at that moment. But if time had a beginning, what came before it? The question may not even make sense because before implies time already existed. Some theories suggest that time is infinite, stretching endlessly into the past and future. Others propose that time is cyclic, repeating in an endless loop. If true, the universe may expand, contract, and restart in a new Big Bang over and over again. Quantum physics adds more complications to the question of time. In the world of tiny particles, time does not always behave as expected. At this scale, events can happen in strange ways that seem to defy normal cause and effect. Particles can be in multiple states at once, and their behavior only becomes definite when observed. Some interpretations of quantum mechanics suggest that time itself may emerge from deeper, timeless processes. If so, time might not be a fundamental feature of the universe, but rather something that appears at larger scales. Time remains one of the greatest mysteries in science. It shapes every experience, yet its true nature is still unknown. It might be an illusion, a fundamental part of reality, or something that emerges from deeper physical laws. The more scientists learn about time, the stranger it seems. Even with all the discoveries of modern physics, the question of what time really is remains unanswered. The idea that the universe could create itself is one of the biggest questions in physics and philosophy. People have always wondered where everything came from. Did the universe always exist, or did it come from nothing? If it came from nothing, how is that possible? Science has theories, but none give a final answer. The Big Bang Theory explains how the universe expanded from a tiny, dense point nearly 14 billion years ago. This theory is backed by strong evidence, like cosmic background radiation and the movement of galaxies. But the Big Bang doesn't explain what caused it. If space, time, and matter all came into existence at that moment, then what triggered it? Some scientists think the universe might have created itself. This idea comes from quantum mechanics, which describes the strange behavior of particles at the smallest scales. In quantum physics, particles can pop in and out of existence without a clear cause. This happens all the time in what's called quantum fluctuations. Space isn't really empty, it has energy, and that energy can produce particles out of nothing for very short periods. Some physicists think the whole universe could have started this way. If tiny particles can appear from nothing, maybe the same rule applies to the entire universe. This is the foundation of the universe from nothing argument. It suggests that the laws of physics allow the universe to appear spontaneously, just like particles do on a small scale. But there's a problem. The universe isn't just a tiny particle, it's huge. If the universe came from nothing, why did it get so big? One idea is inflation. Right after the Big Bang, the universe expanded faster than the speed of light for a very short period. This inflationary period explains why the universe looks the way it does today. But inflation itself needs an explanation. Where did the energy for inflation come from? Some physicists, like Stephen Hawking and James Hartle, propose that time itself may not have existed before the universe. They suggested that time and space are connected, and that before the Big Bang, there was no before. This means asking what happened before the universe is like asking what's north of the North Pole. The question doesn't make sense because the idea of before doesn't apply. Another idea comes from loop quantum gravity, a theory that tries to combine gravity and quantum mechanics. This theory suggests that the universe didn't begin from nothing, but instead bounced from an earlier state. In this view, the universe could be cyclical, expanding and contracting forever. Instead of a single Big Bang, there could have been many. Another approach involves string theory and the idea of a multiverse. If our universe is just one of many, then maybe new universes are constantly forming from the remains of old ones. This means our universe could have come from a previous one in a never-ending cycle. But even if these theories explain how the universe appeared, they don't answer why the laws of physics exist in the first place. If the universe came from nothing, where did the rules that allow it to do so come from? Some physicists argue that the laws of physics could emerge naturally from randomness. Others think they might be as fundamental as logic itself, existing without needing a cause. Some people turn to philosophy and theology for answers. Many religious traditions say that a higher power created the universe. This idea has been around for thousands of years and provides a different kind of explanation, one based on purpose rather than physical laws. But even this raises questions. If a creator made the universe, then where did the creator come from? Does something have to exist forever, or can something truly come from nothing? The debate continues because there's no clear proof for any single answer. Science can explain how things work, but the ultimate why remains open. What we do know is that the universe follows patterns. Whether those patterns came from nothing or have always existed is a question that may never be fully answered. But every time we learn more, we get a little closer to understanding the greatest mystery of all. The idea that we might be living in a simulation has fascinated scientists, philosophers, and the general public for years. Some take it as a joke, while others see it as a serious question about the nature of reality. The thought is simple. What if everything we see, hear, and experience is not real in the way we assume? What if we are inside an advanced computer program, much like a character in a video game? The logic behind this idea comes from advancements in computing and artificial intelligence. Consider how video games have evolved over the past few decades. Early games were simple, with pixelated characters moving on flat screens. Today, video games feature detailed worlds with realistic physics, artificial intelligence, and immersive experiences. If technology continues improving, it's possible that one day we could create a simulation so advanced that the people inside it wouldn't know they were in a simulation. Some scientists and thinkers argue that this may have already happened. The philosopher Nick Bostrom proposed a famous argument known as the simulation hypothesis. He suggests that if civilizations continue to develop technology, they will eventually have enough computing power to simulate entire worlds. If that happens, and many simulated worlds exist, the odds that we are living in the one real world become extremely low. Instead, it would be more likely that we are inside one of the many simulations. Skeptics argue that this is just speculation without evidence. They say that just because something is possible doesn't mean it has happened. We don't have proof that any civilization has created such simulations, and we certainly don't have proof that we are in one. Still, some scientists take the idea seriously and have looked for ways to test it. One approach is to look for glitches or irregularities in the universe. In a video game, glitches happen when the code doesn't work as expected. If we live in a simulation, there might be similar glitches, strange occurrences that hint at an artificial nature. Some researchers point to quantum mechanics as a possible clue. In the quantum world, particles behave unpredictably. They can exist in multiple states at once and seem to change based on observation. Some have speculated that this is like a simulation, only rendering details when they are needed, just as a video game only loads parts of the world when a player looks at them. Another test comes from the idea of computational limits. Even the most advanced computer would have limits on processing power. Some scientists have wondered if these limits might show up in physical laws. If space, time, and energy are divided into tiny finite units like pixels in a game, this could suggest a simulated reality. Experiments in physics have tried to measure whether space itself has a smallest possible size, but so far there is no clear answer. One of the biggest challenges to the simulation idea is explaining why a civilization would create it. If we are in a simulation, who built it? Some imagine advanced beings, perhaps humans from the future, running ancestor simulations to study the past. Others suggest that an unknown intelligence could be experimenting with different versions of reality. It's even possible that the simulated beings, us, are meant for entertainment, much like we create fictional characters for movies and games. This leads to deeper questions about consciousness and free will. If we are in a simulation, do we have control over our actions, or is everything predetermined by the code? Could we ever break out of the simulation? Some have compared this idea to religious beliefs, where a higher power oversees the universe and decides how it runs. The difference is that instead of a spiritual creator, the simulation hypothesis suggests an advanced programmer. Some argue that whether we are in a simulation or not doesn't change anything. If the simulation is perfect, then our experiences are real to us. The world still follows consistent rules, and we still have emotions, relationships, and ambitions. In a way, this makes the question unanswerable. If the simulation is designed well enough, we may never be able to prove or disprove it. Others believe that if we did find out we were in a simulation, it could change how we see life. If we knew that someone or something had designed our world, would that affect how we live? Would it change our morals, our science, or our sense of purpose? Some say it wouldn't matter, while others believe it could shake the foundations of society. For now, the question remains open. Scientists continue to study the nature of reality, but there is no clear proof that we are living in a simulation. The idea remains a mix of philosophy, physics, and speculation. It raises important questions about what reality is and how much we can truly know about the world around us. The idea of a center of the universe is one that seems natural. When we look at everyday objects, they all have a middle. A table has a center. A room has a center. Even the Earth itself has a core. But the universe doesn't work the way everyday objects do. It is vast beyond comprehension, and the way it expands makes the concept of a center difficult to define in the usual way. To understand why, it helps to consider how the universe behaves. The universe is expanding. This idea comes from observations of galaxies moving away from us in every direction. In the early 20th century, astronomers like Edwin Hubble noticed that distant galaxies aren't just drifting around randomly. They are all moving away from each other. The farther away a galaxy is, the faster it moves away. This observation led to the understanding that space itself is stretching, like the surface of a balloon inflating. Imagine a balloon with dots drawn on its surface. If you blow air into it, the dots move away from each other, but none of them is at the center of the expansion. every dot sees the others moving away in the same way. This is similar to how the universe expands. If you were in another galaxy, billions of light years away, you would see galaxies moving away from you, just as we do from Earth. This tells us that the universe has no single point that can be called its center. The expansion happens everywhere at once. People sometimes imagine the Big Bang as an explosion, like a bomb going off in space, throwing matter outward in all directions from a single point. But that isn't accurate. The Big Bang wasn't an explosion in space. It was an expansion of space itself. Every point in the universe was part of the Big Bang. There was no empty space around it. Space itself came into existence and began stretching in all directions at once. If there was a center, it was everywhere at the same time. This is a hard idea to grasp because everything we experience in daily life has a location. When we drop a rock into a pond, ripples spread outward from where the rock hit the water. The center of those ripples is easy to point out. But the universe doesn't behave that way. There is no outside edge for it to expand into. Instead, space expands within itself. If the universe is infinite, it has always been infinite, just changing in scale. If it is finite but unbounded, like the surface of a sphere, it still has no center within the space we exist in. Another way to think about this is to consider the idea of looking for the middle of the Earth's surface. The Earth is a sphere, so you can pick any point and say it is the center from your perspective. Someone on the other side of the world could do the same. Both are correct in their own way. The universe may work in a similar fashion, but in 3 dimensions rather than 2. Scientists use powerful telescopes to look deep into space. The farther we look, the farther back in time we see, because light takes time to travel. Some of the most distant galaxies we can observe are over 13 billion light years away. These galaxies are not at the edge of the universe in a physical sense. They are simply the most distant things we can detect right now. If we were in one of those galaxies, we would see other galaxies moving away from us, just as we do from Earth. That means no matter where you are, the universe looks roughly the same on a large scale. If the universe had a center, then we would expect to see something different in one direction compared to another. We might see galaxies moving away faster in one direction and slower in another. But that's not what we observe. The large-scale structure of the universe appears uniform in every direction. This supports the idea that there is no single center. Some people wonder if the Big Bang happened at a specific place. If the universe had a beginning, shouldn't that point be the center? The problem with this idea is that the Big Bang didn't happen in one spot. It happened everywhere at once. There was no empty space where it occurred. Every part of the universe, no matter where you stand, was once contained in that event. A common misconception is that the universe is expanding into something. It's natural to think about expansion as something growing into empty space, like a balloon filling a room. But space itself is what's expanding. There is no outside edge. If the universe is infinite, then it has always been infinite, just getting less dense over time. The cosmic microwave background, the faint glow left over from the Big Bang, gives us more evidence that there is no center. If the universe had a central point, we might expect this radiation to be stronger in one direction and weaker in another. But it looks almost exactly the same everywhere. The slight differences in temperature that do exist come from small variations in density when the universe was young, not from a central explosion. Some people suggest that the universe might have a shape that allows it to curve back on itself. If this is true, then traveling in one direction far enough might bring you back to where you started. In that case, the universe would be finite, but without an edge, much like the surface of a sphere. But even if this were true, it still wouldn't have a center in the way we think of centers. One question that remains open is what happens at scales beyond what we can observe. Our observable universe is limited by how far light has traveled since the Big Bang. This means there could be regions beyond what we can see. If the universe is infinite, then this goes on forever. If it's finite, it might wrap around itself or extend in ways we don't yet understand. Thinking about the center of the universe forces us to reconsider how we define location and movement in space. Our instincts tell us that everything must have a middle. But the universe doesn't follow the same rules as objects we see in daily life. Space itself is flexible, and its expansion means that no single place can be called the center. No matter where you are, it appears that everything is moving away from you. The deeper we look into space, the more we confirm that every point is just as important as any other. Scientists estimate that billions of planets exist in our galaxy alone, but not all of them can support life. When we talk about habitable planets, we mean planets that have the right conditions for life as we know it. The key factors include liquid water, an atmosphere, and a stable climate. Earth meets all these conditions, but could there be others like it? Astronomers focus on planets in the habitable zone of their stars. This is the region where temperatures allow liquid water to exist on the surface. Too close to the star and the water evaporates. Too far and it freezes. Our own solar system provides a good example. Venus is too hot and Mars is too cold, but Earth sits in just the right spot. This idea helps scientists narrow down their search in other star systems. Advancements in telescope technology have allowed astronomers to identify thousands of exoplanets, planets outside our solar system. NASA's Kepler Space Telescope played a major role in this discovery. Launched in 2009, Kepler found over 2,600 confirmed exoplanets before it was retired. Many of these were gas giants like Jupiter, but some were rocky planets in their star's habitable zone. This was the first real evidence that Earth-like planets could be common. The TRAPPIST-1 system is one of the most exciting discoveries. It contains 7 Earth-sized planets orbiting a red dwarf star about 40 light-years away. 3 of these planets are in the habitable zone, where liquid water could exist. Because red dwarf stars are smaller and cooler than our Sun, their habitable zones are much closer. This means planets in these zones experience stronger radiation and gravitational effects. Scientists are still studying whether these conditions make life more or less likely. The James Webb Space Telescope, launched in 2021, is helping scientists analyze these exoplanets in more detail. It can detect gases in their atmospheres, such as oxygen, methane, and carbon dioxide. These gases can be signs of biological activity. If a planet's atmosphere has a mix of these gases similar to Earth's, it could indicate the presence of life. Another way scientists estimate the number of habitable planets is by looking at our own galaxy. The Milky Way has over 100 billion stars, and many of them have planets. Based on Kepler data, astronomers believe that 1 in 5 Sun-like stars has at least one planet in the habitable zone. If this estimate is correct, there could be tens of billions of potentially habitable planets in our galaxy. However, not all habitable planets will be like Earth. Some might be water worlds, covered entirely by oceans. Others might have thick atmospheres with extreme weather patterns. Some planets could have conditions we haven't even considered yet. Life on these planets might look very different from what we know. It could be microscopic or thrive in extreme environments, much like bacteria in Earth's deep oceans or underground caves. Mars is a good example of how habitability can change over time. Scientists believe Mars once had rivers, lakes, and even an ocean. But over billions of years, it lost most of its atmosphere, and its water evaporated into space or froze underground. If life ever existed there, it would have had to adapt to extreme conditions. NASA's Perseverance rover is searching for evidence of past life by studying rocks and soil in an ancient lake bed. Some moons in our solar system also have potential for life. Europa, a moon of Jupiter, has a thick icy shell with a subsurface ocean beneath it. Scientists believe tidal forces from Jupiter's gravity create heat, keeping the water liquid. This could provide a stable environment for life, even without sunlight. Saturn's moon Enceladus also has a subsurface ocean, and geysers on its surface eject water into space. These moons challenge the idea that a planet must be in the habitable zone to support life. The search for habitable planets is not just about finding another Earth. It's about understanding the conditions that make life possible. Even if we find planets with the right conditions, we won't know for sure if they have life until we can study them up close. Future space missions might send robotic probes or even humans to explore these distant worlds. Some scientists believe that the discovery of alien life is inevitable. With so many planets out there, It seems unlikely that Earth is the only place where life has developed. Others argue that life might be much rarer than we think. Even if a planet has the right conditions, the process of life emerging could be extremely rare. The search continues, and each new discovery brings us closer to understanding our place in the universe. The number of habitable planets is likely vast, but the true question remains, are we alone? The universe is vast and full of mysteries. Scientists have been studying it for centuries, yet there is still much we don't know. Every new discovery leads to more questions. Some believe that one day we will understand everything. Others think that the universe is too complex for human minds to fully grasp. The question remains, will we ever understand the cosmos? People once thought Earth was the center of everything. Then, we learned that Earth orbits the Sun. Later, we discovered that the Sun is just one of many stars in a huge galaxy. Over time, we found out that the Milky Way is one of billions of galaxies. With each discovery, our understanding grew. But each step forward also revealed how much more there is to learn. One of the biggest challenges in understanding the universe is its size. The observable universe stretches for about 93 billion light years. That means the light from the farthest objects we can see has been traveling for billions of years. Beyond that, there may be even more, but we can't see it yet. This raises a question. If we can only observe part of the universe, can we ever claim to understand all of it? Another challenge is dark matter and dark energy. Scientists believe that about 95% of the universe is made up of these unknown substances. We can't see them, but we can detect their effects. Dark matter seems to hold galaxies together, while dark energy is causing the universe to expand faster. Despite decades of research, we still don't know what these things are. If we don't understand most of the universe's mass and energy, how close are we to understanding the cosmos? Black holes are another mystery. When a massive star collapses, it forms a black hole. These objects have such strong gravity that nothing can escape them, not even light. Scientists have learned a lot about black holes, but many questions remain. What happens inside one? Do they destroy information, or is there a way for it to escape? Some theories suggest black holes might connect to other universes. If true, this would change everything we know about reality. Time is another concept we struggle to understand. We experience time as a constant flow from past to future. But Einstein's theory of relativity shows that time moves differently depending on gravity and speed. In strong gravity, time slows down. This has been proven with satellites and astronauts. But what does this mean for the universe? Could time itself be an illusion? If we don't fully grasp time, can we ever claim to understand the cosmos? The nature of space itself is another puzzle. Most people think of space as empty, but scientists have found that it is not truly empty. Even in a vacuum, tiny particles appear and disappear. Some theories suggest space is made of tiny building blocks, like pixels on a screen. If true, this would mean space is not smooth, but made of tiny pieces. Understanding space at this level could change everything we know about physics. There is also the question of extraterrestrial life. Many scientists believe life must exist elsewhere. The universe contains billions of galaxies, each with billions of stars and even more planets. Some of these planets are similar to Earth. If life started here, why wouldn't it start elsewhere? But despite years of searching, we have found no proof of alien life. If we never find it, does that mean we are alone, or does it mean we aren't looking in the right way? Another challenge in understanding the universe is the limits of human knowledge. Our brains evolved to understand the world around us. We can grasp things like gravity, heat, and motion because they affect our daily lives. But the universe operates on scales we are not built to comprehend. Quantum mechanics describes particles that can be in two places at once. Relativity describes space and time bending like a fabric. These ideas are not things we can easily picture. If the universe follows rules that don't match our intuition, will we ever fully understand it? Technology is another factor. Our understanding of the cosmos depends on the tools we use to study it. The telescope changed our view of the universe by allowing us to see distant planets and stars. Space probes have traveled beyond our solar system, sending back data we could never get from Earth. The James Webb Space Telescope is revealing parts of the universe we've never seen before. But even with these tools, there are limits. Light from distant objects takes time to reach us. The farther we look, the older the light. We will never see the present state of the entire universe, only its past. Some theories suggest the universe may be infinite. If this is true, can we ever understand something that has no end? Imagine trying to count all the grains of sand on every beach on Earth. Now multiply that by infinity. The task becomes impossible. If the universe is truly endless, then by definition, we can never fully understand it. There is also the idea that the universe might be a simulation. Some scientists and philosophers suggest that our reality could be a complex program running on an advanced computer. If this were true, the laws of physics might not be fundamental, but instead programmed rules. If we are inside a simulation, can we ever learn the truth? And if we did, what would that mean for our understanding of the cosmos? Another possibility is that the universe is constantly changing. The laws of physics might not be fixed, but could evolve over time. If true, this means that what we understand today might not apply in the distant future. It would also mean that any complete understanding of the universe would only be temporary. Scientists have already observed changes in fundamental constants over long periods. If the universe itself is evolving, then understanding it might always be a moving target. Some people argue that understanding the cosmos is not about having all the answers, but about continuously learning. Science is a process, not an endpoint. We may never reach a final theory that explains everything, but each discovery brings us closer to deeper knowledge. Even if we never understand the cosmos completely, the pursuit of knowledge itself may be the most important part of the journey. For now, we continue to search. Telescopes scan the sky, looking for distant galaxies. Scientists develop new theories, testing them against the evidence. Probes explore the solar system, sending back data that helps refine our understanding. Each step brings us closer, even as new questions arise. The universe remains a vast, mysterious place, and our quest to understand it continues.